Hello, everyone. So we are starting the second workshop for learning 3D with multi-view supervision at CPR. Last workshop was at CPR 2023 in Vancouver. We had a much bigger room, actually the biggest like hall, but now they gave us the smallest room, but it's more stacked, so that's good. Okay, so let me introduce myself. I'm Abdul Hamdi, a postdoc at the VGG group in University of Oxford. I'm co-organizing this workshop with my colleagues from VGG and also my former colleagues in KAUST, where I did my PhD. So Gordon, Shwantia, Silvio, Sarah, Genji, Yash, and Bernard. So just a brief intro about the topic and why are we actually doing this workshop. We are entering into this era of spatial indoor computing, and it's actually now the hottest. It used to be like self-driving cars, and outdoor was the hottest topic in computer vision, but now everyone is shifting to indoor, and it's becoming more and more important in many of the applications that we're seeing every day. And these spatial computing is a fancy word. I would say it's computer vision plus computer graphics in indoor situations for both robotics and for XR applications. So this is what they teach in textbooks about, like, computer vision is about taking images and getting into the intrinsics, and computer graphics about taking these intrinsic, extrinsics, or like these latent variables and giving you the output image. For me, I have a different concept of how these things play. Sorry. So for me, vision is much broader than that. It's more of what science is trying to achieve. You look into observation, and then you want to get into the reality or the truth, which is consistent, universal, and lasting. Graphics is about taking some items, properties, and relations, and then doing this R or G, rendering or generation functions, to give us the metaverse. Or this is what the ultimate goal of graphics, in my opinion. So in vision, the problem is we don't have access to reality or truth, because this is actually hidden. This is what we are trying to get into. So we replace it with what we call ground truth, what I call meta-reality. These are very unique representations that try to deconstruct how reality looked like. And when I show this to Andrew Zisserman, he disagreed that we are trying to deconstruct meta-reality. He thinks we are actually reconstructing the meta-reality. I think these, for example, like class labels, mesh vertices, or segmentation labels are quite artificial in a sense that they don't have an actual representation in real world. We're not reconstructing an atom by atom or real world. So these concepts are actually borrowed from computer graphics. So the items, the properties, the mesh vertices, this is how people in computer graphics use to render and generate their metaverse. So we are borrowing these to construct our meta-reality in computer vision. But also the observations we collect in computer vision, like the data sets and our deconstruction functions, like AlexNet or VIT or whatever, they tend to be actually very useful in the graphics pipeline, and vice versa. So whenever people in graphics develop new items, properties, and relationships in their representations, we develop them into our meta-reality, and the whole computer vision pipeline actually develops. So they're quite intertwined processes. And the core idea here is that the more we have of these observations and the more developed and our meta-reality and our computer vision, it fuels these two pipelines together. Why am I talking about this? Well, 3DMV, which is the topic of our workshop, is summarized in this pipeline. And I think this is the first, in my opinion, 3DMV paper, in a sense that it has the elements of our interest in this workshop. So it has the R function, the rendering function. It has the F function, And it was the first paper that used deep learning in a 3D MV scenario. That means you do like rendering, you do the deconstruction function, and then you develop a full pipeline that leverages both functions and like a deconstruction function to get into your goal, whatever that goal is. Uh, Currently, 3D MV, in my opinion, is witnessing a new boom, and that's because of the latest developments in foundation models for 2D image generation and understanding. These models led to the latest wave that we have witnessed lately in improved generation for 3D content, as well as for 3D understanding for zero shot setting or settings that they were not feasible before these foundation models in 2D vision. Sorry, I keep hearing this weird sound. And this is actually witnessed by, if you just look at the statistics, if you just search in the, I don't know how many papers in the CVPR, you can see like 437 papers that have 3D, multi-view 43 papers, and video, that just for reference to other topics that are ongoing, 285. I'm pretty sure if you go back like 2 or 3 years ago, those numbers would have been way different, even with if you take into account the increase of number of papers. During this last year, we witnessed a lot of developments in this direction, leveraging 2D foundation models for 3D understanding and generation. So this was a Magic 123 paper in which I was involved in. Took these like foundation models, either the 2D or 3D, and tried to improve the performance of image to 3D. At that time, those results looked very cool, not anymore, of course, 1 year later. But also, we witnessed during this last year, like huge development in multi-view diffusion models. So very strong 3D priors that were not feasible before, but also development into representation learning. So 3D representations that are actually very efficient. They work for novel view synthesis, 3D understanding, and 3D generation very well. Also in this conference, actually we have an oral presentation today for Duster. The authors will present their work. They didn't give them an oral at CVPR, so we give them an oral at our workshop because they deserve it. So it's a paper that basically learned a stereo vision model that can work very well in estimating depth, properties of the cameras, poses, intrinsics and extrinsics very well in very sparse setup, which was extreme. Uh, Hello? Actually, it's working. My heart stopped for a second. Okay, so yeah, you never know. Yeah, so Duster is actually, in my opinion, a breakthrough in 3D computer vision and in this era of 3D MV, like leveraging foundation models that work very well in 3D and multi-view setups. But we're also entering into the era of 4D vision. So if you noticed in the last year, so many papers about either 4D data sets or 4D generative models that were not thinkable, let's say 2 or 3 years ago. Nobody was trying to generate 4D because 3D was not working. But since we reached to the point where 3D start to work, people now try to look into 4D as well. And it's actually one of the topics that we're interested in this workshop. So many of the speakers will talk about their 4D works. So in summary, our topics will cover multi-view for 3D understanding, predicting camera poses, multi-view for 3D generation and novel view synthesis, and also 4D generation with multi-view models. Some challenges people speak of during their talks, how to leverage 2D priors, how to leverage 3D priors for 4D, sparse views, inconsistent generation of multi-view diffusions. So this is like one of the core challenges right now the community is trying to tackle, and how to get strong 3D priors, and also the efficiency. And this is reflected in the speakers and their topics that we will be addressing. This is the schedule for today. So we'll have 2 keynote speakers, and then we'll go for a coffee break, come back for 1 keynote, and then we'll go for lunch break. We'll come back for oral sessions, poster sessions, and another coffee break, 2 keynotes, and then we'll conclude with a panel discussion. We will have 5 orals starting at 1 p.m. With Duster, the first one, Ginny, 2 invited orals at our workshop, and then 3 orals from the 25 papers accepted at our workshop. All of the details you can find are in the website. You can find it in the website, also in the booklet they give you for CPR. And yeah. We have 25 papers accepted. 18 of them are published in the proceedings. You can find all of that in the website as well. All posters, please, if you have posters, it's not in this building, it's in the Arch building. So you have to go and mount your posters around the time the poster session, which is 2 p.m. So you can do that like maybe 10 minutes before the poster session. And it will be up to 3 p.m. But we have a coffee break at 3 to 3:30, so you can stay there, I would say, up to 3:30, but please, after 3:30 p.m., you have to remove the posters because there are other poster sessions from other workshops in the same time and the same location. So please try to respect other people's poster sessions. There will be prizes provided by KAUST for best papers and best paper runner-up, similar to last year. Our sponsors last year were Luma, when they didn't have all of that fame that they're having now. So they decided maybe they're bigger than our workshop this time. But I'm pretty sure we have very good relationship with them until now. Yeah. This is a Nat Geo documentary about KAUST. If you would like to know more about KAUST, if you just search in YouTube Chasing Answers, KAUST, or Nat Geo KAUST, you will find a documentary of 3 episodes showing. You will find very interesting 3 documentaries about KAUST. There will be a vote for best poster. We'll also share the link later during the poster session. But if you want to take picture for it now, and yeah, just for your reference, you can vote later for the best posters. Oh, sorry. Some people were taking pictures. Again, I would like to thank the organizers who put a lot of effort into this, and without them, this workshop would have not happened. And with that, I let my colleague Sarah introduce the speakers. Thank you.
Hello, good morning. Our first speaker is Professor Matthias Nisner, a leading figure in the field of 3D computer vision and computer graphics. Professor Nisner heads the Visual Computer Lab at Technical University of Munich, where his research focuses on 3D reconstruction, semantic 3D scene understanding, video editing, and AI-driven video synthesis. Professor Nisner is also a co-founder of Synthesia, a startup focusing on AI-driven synthetic media. Let's welcome Professor Nisner to the stage.
You need sound.
Okay, thanks a lot. Wow, well, I have to figure out quickly one thing. We have to figure out what one scene at the same time. Time of this. Okay, a lot of people in Zoom too. Wait, audio? What can I highlight this? Yeah, this. All right, it's fine. All right, we'll go with that. Cool. So thanks so much. I think this is probably one of the first workshops right now, the CVPR. It's really a pleasure to have so many people here. Thanks to the organizers for bringing everybody together. So in this talk, I'm going to basically come from the other direction. We're going to talk a little bit about the 3D stuff, how we get it, and then basically how we use it for the multi-view later on as priors. And the main motivation of this talk is basically how do we create immersive worlds with AI in 3D. And I'm going to have a bit of a controversial discussion at the end. Also, what is the right representation to do that? Do we need diffusion models? Do we need 3D foundation models and so on? So my dream basically is we want to get video games and movies that are as realistic as the real world. And the big question is obviously how do we get the 3D content for it? I mean, rendering and so on has made a lot of progress, but getting the underlying content is really, really challenging. And despite there being a lot of progress in the recent years, I think this is still a very open topic because a lot of the AI models, they produce some stuff, but I'm going to argue there's a lot of shortcomings we still have to cover. So when I started 3D content creation, I thought, well, we just do 3D reconstruction. So in 2011, the Microsoft Kinect came out, and I think this was a big inspiration for many people. This was like this Kinect Fusion work from Richard Newcomb and colleagues. And the idea was basically you have a Kinect in real time, you can get these kind of reconstructions. And we thought, well, I mean, this is awesome. Now we take these depth sensors and we reconstruct 3D scenes in real time. And one of the works that I was involved at the time was this voxel hashing work. And the idea basically there is you have an RGBD stream, right? So you get color and depth at the same time. And you get here at the bottom, you get a real-time 3D reconstruction of a scene. This scene is a signed distance field, right? So you have in every voxel, essentially, you're storing a signed distance value. And for every signed distance value, you know how far the surface is away. And based on that, you can do an isosurface extraction with marching cubes, and you can get a 3D mesh out of it. And typically, you could get meshes to look something like this. And you could get this in real time. And, you know, at the time being, I think this was relatively impressive, I think. So we could actually get relatively large environments as well. We could reconstruct them in real time, and we could also do some sort of, you know, physics-based, collision-based interaction and so on with these scenes. Now, the idea was, why I was very interested in the real-time aspect was we thought, well, we're going to do just a lot of 3D scanning, and we just check out where we're missing pieces, and eventually we're going to get a pretty good 3D model out of it. And for research papers, we showed results like these. And the results we didn't show in the research papers was results like this. Because the problem is, despite the fact that you're trying really, really hard to get 3D scans, the real issue is you just miss a bunch of stuff. And there might be many reasons why you're missing a bunch of stuff. And one reason why you're missing stuff is like sometimes you can't get there with a sensor. And just sometimes it's very, very difficult for some parts of the area to be reconstructed at all. For instance, if you have like a black leather couch for like RGBD sensors, like the Kinect, it was very difficult to get any 3D surface reconstructions. And for us, this was kind of, you know, a starting point where we realized, well, no matter how good of a job we're going to do at 3D scanning, in multi-view stereo reconstruction is in a sense the same problem. We're never going to get 3D models this way that we can actually put in a video game. It's just never going to be good enough if you just use these outputs. And I still stick to the same statement that I made at the time. It's like, it's very tricky that this one will ever reach the quality of an artist that creates 3D models. It's just very difficult. So the obvious thing, what we thought then is, well, okay, neural networks are pretty cool. And at the time, people have tried a lot of generative networks in 2D. Can we actually go ahead and take these 3D scans and kind of fix them up? So we take 3D generative models, And we thought, well, maybe there's a way of you know, filling in some holes, doing some shape completion, and eventually getting something that is, you know, at least close to artist level quality. So we started actually very simple here. We started on a shape basis. So this is on ShapeNet. This is already 2017 CVPR paper. This was quite a while ago, 7 years ago. And the idea is you take a partial scan and you do some sort of completion on top of it. And the idea is this is a simplified version of a generative model, right? Because it's conditional and you already have well, you have a lot of constraints basically. So this is kind of a quote unquote easy problem to deal with. It's easy in a sense that you only have to fill in a bunch of pieces. It's difficult in a sense that you need synthetic ground truth data to train it. So that's kind of the pro and con of these two things. But if you look at a problem like this, you can go and take a partial scan. Here's input. You do some sort of like auto encoder network to predict the sign distance function that is complete. And you're trying to basically minimize the unknown space that you hadn't observed before, and you're trying to go ahead and get a shape completion. And in fact, this is actually super straightforward what we've done there. So nowadays you can't publish papers like this anymore, but at the time this was really easy. So you basically go ahead and have a 32 cube volume. Each voxel stores a distance value. In fact, the input is a sign distance value and an observed space, observed state. And minor issues. Okay. Can people still hear me? Maybe not. Better? Okay, we're back. Yay. Generative audio. Okay. Yeah, so, but the high level thing is it's really straightforward, right? This is just a 3D unit, basically. You have an autoencoder structure, you have a bunch of skip connections. We did a bunch of stuff like, you know, including semantic features and so on. It helped a little bit, didn't help that much. But at the end of the day, you can get completions that look like these ones. So this is basically, you have an input, you have a partial shape, right? You have some sort of completion, you're gonna get some shape as output, and it looks not too bad. And as I mentioned, this is a relatively simple task right now, right? I mean, we're running this on a 32 cubed volume, which is like, nobody would, you know, would think this is good enough anymore. And the thing that was interesting, in this case, we didn't use any like real generative loss in a sense. So this was not a GAN, this was just an autoencoder, this was just an L1 loss at the reconstruction of the distance values. But if you have enough condition given, then you can actually do something reasonable about it. But now, of course, the field has moved quite forward, right? We actually have very, very powerful 3D models. We have powerful losses that we can apply. We have GANs for the most part, but we also have very recently, since the last 2 years, with like, you know, a lot of success of diffusion models in 2D, you can actually do also diffusion in 3D for similar tasks. And now, instead of using a conditional task, you can even go ahead and use diffusion models to do full 3D shape generation, right? You can generate it based on, you know, some conditioning, or you can also use it for reconstruction tasks where you take stuff like a point cloud as input. And this was a paper last year we had at SIGGRAPH. So a paper from Biao Zhang. He's in Peter Wonka's group in KAUST. And he has been developing this model basically where you can go ahead and have a 3D diffusion model that takes as input, for instance, a point cloud. You compress the input shape into a sequence. Then you have some, in this compressed sequence, you have sort of a cross attention, and then you decode the sequence as a continuous function, right? And this whole thing can be trained end to end. You do your multiple diffusion rounds, and eventually you're going to get a very, very good isosurface as an output. You can do this basically with all kind of continuous functions, with implicit representations, distance fields, occupancies, and stuff like this. You can use it for various types of conditions, for instance, as a point cloud as input, and you can also get a pretty good reconstruction. And if you're looking at some of these results, you can already see the quality actually got a lot better, a hell lot better actually, what anybody did before, right? So this is like not just a simple L1 loss anymore, you have like a proper formulation in the diffusion model, and you can actually get pretty good reconstructions like this. Here's a few more examples, right? You see already, now we have very fine scale structures here. The chair can be pretty faithfully reconstructed. A few more. And this is, I think, at the level where, you know, it's kind of getting close to what might be useful, right? I'm going to tell you later why this is still not useful, but it looks a lot better what people had before. The obvious problem, what people complain about this is all on like single shapes, right? Like this is far away from doing this on like large scenes. So one of the big questions is actually, can you go ahead and scale this stuff up and work on large 3D scene environments? And the answer is yes. And the way you make this work is you basically borrow the same ideas what people had been doing for 2D diffusion models. So what you can do is you basically operate in latents. And the whole point why latent diffusion is a big thing is because these latents, they kind of split up the training process into two parts, right? So you first train this autoencoder. So there's various GANs formulations what people are using, but you basically have an autoencoder that gives you the latents, and then you train the diffusion model in the latent codes. And the whole point is this makes the whole thing much more scalable. And we have some ongoing work right now where we're trying to do this at the scene level. So basically not just in objects anymore, right, but generate like entirely large scenes. And there's a couple of things what we're doing here. We actually have a 3D scene. So first of all, we have to figure out how to, split the scenes into chunks. And then we operate on a per chunk basis. And within each chunk, we have kind of a grid representation. And this grid representation, we have these latent codes. And then what you do is you need some sort of decomposition in this local chunk that makes sure that you can both generate big structures and fine scale detail. And the way you practice do this is you have a hierarchical representation. So you try at different hierarchy levels, and then you take the respective previous hierarchy level as condition for the next hierarchy level. And on each hierarchy level, you run some diffusion, and eventually you're going to get to a 3D scene. And in this work, this is still ongoing work, this is not fully completed, but the high level idea is that we kind of have a data structure that makes sure this hierarchy works, and we also run this on a per chunk basis. And then overall, we have this latent 3D scene representation where we now have latent codes on a 3D basis. This is still trained on full supervision. So we're training this on synthetic 3D data sets right now, like 3D front and stuff like this. It still operates on distance fields. It still operates where you have to afterwards do margin cubes reconstruction. Okay, but you get results like these. So this is like the current reconstruction that you have. And then what it does is basically it synthesizes chunk by chunk here, right? So you basically diffuse. You generate a bunch of stuff, and you're gonna get, a couple of scenes reconstructed at the end. And yeah, in this way, basically, you can generate pretty large environments actually now with an unconditional model at the moment. You can actually also use the same model and make it conditional, right? You can take some partial point clouds as input, can do some reconstruction. But the point is this is kind of this infinite scene synthesis, right? So you have kind of a couple of things given, and then you just take the previous chunks you synthesized as condition for the next ones, and you just can go on and go on. There's a lot of things what we haven't done yet. I mean, there's a lot of things you can incorporate, like, what kind of rooms you want to do, what kind of structure these rooms should have, and so on. But I think this is pretty exciting right now that you can actually run diffusion models actually in 3D, and you can run them actually on a scene scale. And what's also important here to notice is, like in 3D, it's a little bit different than in an image. So an image has a fixed resolution, right? Like there's a boundary on the image. But in 3D, you don't know how big the scenes are. So every training sample and every inference part is actually completely different. So you need to have some way of like deciding where to start and where to stop. So I think this is pretty exciting. So 3D generative models are pretty good for 3D generation. However, there's still a big drawback of all of these works right now. And the biggest drawback, what I'm always trying to say is implicit surfaces are not enough. And when I say implicit surfaces, I mean this whole concept of using marching cubes on top of a signed distance field of an occupancy grid and so on. So here's this is some early result from the scan completed. It was an earlier version that we had. The problem is basically whenever you're running marching cubes, you're going to get a triangle soup out of it. And this will fundamentally look different from what people use in video games and movies because it's just not very compact, right? So if you're looking around these walls here, like these walls here have basically a few triangles, right? And you can, with a few triangles, you can represent a whole wall. But with the marching cubes meshes, you're getting out of these like, diffusion models and 3D reconstruction methods, you're just never going to get this. So the main problem what you have is you have this triangle soup and you would love to convert it to a mesh somehow, right? And even if you look at current models here, like Get3D, I think is, in my opinion, one of the really fundamental methods that came out for 3D generation. They have the same problem, right? So if you run the method, you get something like this in the middle. It's like 24K faces. And as soon as you decimate the stuff to, let's say, 400 faces, yes, you can decimate it. But the problem what you're going to get is you're just missing a bunch of stuff, right? You're never going to get hard edges here. And this is very tricky. And I mean, the geometric processing community in computer graphics has tried a lot of work for like decades to make sure this process works. But it's incredibly difficult to get anything useful out of this, at least not for content creation. So, and this is why one part of this talk is actually dedicated to argue that I think 3D meshes are really key. So if you're looking at the mesh structure of a room like this, right, you have very, very few triangles, or in this case quads, and very few polygons that actually represent the surface. And I'm going to argue two things. First of all, it's very compact to store the stuff, but I'm also going to argue later it's very efficient to render the stuff. And there's many reasons why it's efficient to render it. Of course, GPUs are designed for that, but there's a reason why this rendering is just much faster and more efficient than if you compare it to like NeRF or 3D Gaussians and stuff like this. So we're going to have a bit of a controversial discussion at the end. However, I want to now explain how can we actually generate these meshes directly. And there's a reason why people are kind of shying away from mesh generation. And the reason is simple, like gradients is kind of an issue there. You have a lot of topology issue, you have a lot of connectivity issues, and it's very tricky in this unstructured representation to formulate a generative model, right? That's why people use signed distance fields. Signed distance fields, great for gradients, very smooth, right? Just meshes, yeah, it's hard to do it with meshes directly. And I wanted to show you one early project on mesh generation. So this was a project we've done in 2019, it's 5 years ago. And yeah, I mean, it looks a bit embarrassing, almost how it looks like right now. But this was the best we could do at the time. So this was a super simple neural network. So here we started with a 3D scan as input. On this 3D scan, we have a graph model, basically. So we first have an encoder, and then we have a graph model that goes ahead and generates first the vertices and the edges. And once you have the vertices and the edges, you have another graph model that goes ahead and connects the dual graph on top of the edges in order to formulate faces. So I want to show this in a little bit more detail how this works and how difficult the problem is actually. So in this case, you have an input scan that's a signed distance field. That could be, you know, it's basically converting a signed distance field into a mesh. That's kind of the high level idea here, right? Then you have some sort of encoder. The first thing is you're going to do, you predict vertices. In this case, we predict 100 vertices. That's the best we could do at the time. And then what you do is you go ahead and just literally connect every vertex with every other vertex, right? So it's an n-squared problem. And you literally have a binary cross entropy for every edge, and you classify whether this edge exists or not. And the underlying network here is a graph, right? So you have a graph neural network with message passing, and you just classify whether edges exist or whether they don't exist. Okay, the tricky thing then, so this is a squared problem, this is a quadratic problem, right? How many edges exist based on the vertices? And now the tricky thing is, how do you do the faces? Well, with the faces, you can do the same combinatorics. So now you take the dual graph and you say, based on the number of edges that you have, how many possible faces can exist? And that's an n-choose-3 problem for triangles. So this is actually a cubic problem. And this is a little bit tricky in terms of compute, but you can do the same thing there, right? For every face, you just classify, does this face exist or does it not exist? And run a binary cross entropy on top of it, and that's it. So you have two independent networks here, you can train the whole thing, and you can get some outputs. And now you also notice why we have 100 vertices here, because we just can't have more combinatorics for the faces. This is the big problem, because this grows cubically. And yeah, we could resolve like these ones. It's kind of funny. So what we had to do is we take a 3D data set. In this case, we took ShapeNet, what we always do. And then what we do is we simplify the whole thing to have only shapes with 100 vertices. Admittedly, that leads to a lot of artifacts in itself already. But then you do basically this graph connectivity, you get the predicted meshes, and then you compare it with the ground truth, because you know which faces and which edges do exist, and then you get some outputs here. And this was the early stage. This was 2019, right? It's not so long ago, and we tried really hard to get there, and this was just very tricky to make it work. But now, of course, there's a bunch of different things that have evolved. So first of all, we have better architectures globally, and we have better loss functions. So I want to show you the same thing what I've shown you for the signed distance field. So here you start with a binary cross entropy loss. Now we want to also go ahead and use diffusion models here and figure out how to actually do some diffusion in order to generate meshes. Now you might ask, well, how do we do that? Okay, so this is also some super interesting work. It's called Polydiff. This is Antonio Allegro. He's a PhD in Tatiana Tomasi's group. And the idea there is you want to go ahead and run essentially a triangle generator. So we're going to start only with triangles. And what you do is you start by defining the diffusion process here. You have a forward and a backward pass, basically. And what you do is you just assume you have a bunch of triangles given, but you don't know where the triangles are. So this one kind of detaches the whole vertex and edge generation. It just ditches this one and just works on triangles directly. So you have kind of a triangle soup, right? You have random triangles. They're somewhere in space based on where they are. This is what we have here. This is our noise. And then what we want to do is we want to denoise the whole thing in order to convert this triangle soup into our respective ground truth samples. Okay, and at inference time, of course, then you do the same thing, right? You start with random noise. It's a purely unconditional process here. And from this unconditional process, you essentially do the inference and get the 3D shapes predicted. Yeah, the whole process looks something like this. So you start with chaos, and eventually you see that the shape structures are going to form eventually, right? Okay, I want to go into a little bit of detail, not too much. The way to get this to work is basically you start with quantized triangles. So, right, so the whole point is everything has to be quantized, otherwise the stuff doesn't run. If you run this on full like floating point stuff and so on, this is difficult. You have the triangles given. You treat every triangle here independently right now during the diffusion process. You get the respective triangle coordinates. This is what you see here. These are the triangles. And then you go ahead and you just add Gaussian noise to it. This is the quantized triangle soup noise at one time step, basically less. And then you have a denoising network that learns how to go from one step to the next step. To be more precise here, the denoising network is a transformer blocks, because that's what everybody uses right now. You have the noise at step t here. And then you predict the respective next step here, right? And at the end of the day, you have the denoised version, you have the target. And what you do for the target is you have a binary cross entropy that tells you whether this thing exists, right? So you have this cross entropy loss at the end of the day that makes sure the triangles you predicted in this denoising process are giving you the respective results. Okay, so here's a couple of more examples, right? This runs faster, but my PowerPoint can't play this, unfortunately. Anyway, so you get pretty good results. And we have also a lot of analysis here that these are actually novel shapes. So these are not just doing retrieval. So when you started this, the tricky thing, of course, when you train this at the beginning, what you're going to get is you literally replicate your training set. And then, we had to make sure this doesn't work anymore. This quantization was a big deal to make this work. You need a bit of augmentation of the data, which is a problem because there's not so much data to begin with in these training sets. So this one is training relatively small amounts of data, but I have I don't think there's a big challenge to train this on larger data sets like Observerse, Observerse XL and stuff like this. Okay, so here's a few more generations. So we basically show that we're generating ground truth meshes, and you can see right now, these ones are pretty compact, right? So you see if you look in here, right? So this is very, very compact. This plane, the seed plane, is basically just two triangles at the end here, which I think is a really big achievement compared to what we had before with the sign distance-based or any other implicit representations. Okay, we have a few more examples. Same thing here, right? You see this is very compact. This is kind of the high-level idea of what we wanted to do. Okay, we have another one here. And so on. A few more examples. Okay, so with that one, I wanted to give one of my PhD students, Javor Sticky, a chance also to talk about some of his work. So he's going to talk about a better version, actually, probably to do this, basically by using large language models to do mesh generation.
Thank you, Matthias. So diffusion is cool, and that's one way to do generation, but I'm going to talk about like another popular way people are doing generative models, and that's using large language models. And we've already seen large language models generate languages. You've seen them generate like code, like you've seen them generate videos, images. But can we use them to generate meshes, right? Like, so this was what our project Mesh GPT was about. Like, let's try to use large language models, at least GPTs, to generate meshes, right? Like, so it's in a sequential way, just like languages are generated. So just a high level overview of what's happening here. And this is like how most of these like large language models also work, right? Like you have a two-phase process where you're first learning vocabulary. In large language model domain, it's called like tokenizers, and that's not what we mainly focus on, but like here it's important because you're moving to a completely different vocabulary, right? Like it's meshes now. So the idea is simple here. You have a shape data set, and you're trying to train an encoder decoder model here, which is basically a face encoder that uses some sort of an embedded code book. So quantization happening here, which is decoded back to the shape data set. And the idea is like at the end of the training, you'll have an embedding code book that basically can be used later on for the transformer phase and make up the vocabulary. So once this done, you train the GPT like transformer and like pass it through the decoder. And just by sequence generating these tokens, decoding them, you can get meshes out of it. So I want to get into a little bit more detail on what's happening here in these two phases. The first one being the generation of this geometric vocabulary, and later on how you train the transformer. So learning the geometric vocabulary. So you have the input mesh, and similar to like the early paper that Matthias showed with the meshes, we're again making a graph out of the mesh. You're treating the faces of the mesh as nodes. So all the faces are nodes, and whichever faces are next to each other, they're treated as like there's an edge between them, okay? So you extract some sort of input features here, like these can be like, I don't know, the area of the triangle, it could be the vertices, and all sorts of stats you can have, like what do you think would be helpful later on for reconstruction? You pass it through a graph convolutional encoder, which extracts features per face here. And then you pass it to something that's a residual quantization module. And what's happening inside this module is you take the features on the face, which we just extracted with the graph convolution encoder. You distribute them across vertices. And when you do that, you'll see that some of the triangles will be next to each other, right? So, and this is one vertex which is shared between two triangles. So you want to kind of aggregate that. And this is what happens here. And this we find that is something very important that you have to aggregate, like it really affects the performance, right? Like, so the FID here goes wild if you do it per face or per vertex. Then you take these features, you quantize it, and this is like from the days of teaming transformer, right? Like you're trying to quantize the features so that you can use it later on in the transformer phase. And one thing we do different here is use residual quantization, which is assigning for one feature, multiple features in the code book. And this is again, very important, right? Like, so for me, this reconstruction phase didn't even work if I didn't use residual quantization. It's just like getting more capacity in the code book here. Once you have this, you put the face features back. And for the reconstruction phases, you have to sequence them because later on we'll see transformer generates sequences. The graph structure is lost. So you cannot rely on the graph structure anymore. You're just sequencing phases. We do it in an order of like from the ground up. So that's the sequence of the mesh. And you pass it through a 1D resonant decoder, you get the coordinates back, and you just have some sort of reconstruction loss here that supervises the whole thing. So you train all this is done. Now you have a really nice code book that you can use for training a transformer. And this is like a very simple transformer. We use the GPT-2 medium architecture here. We pass it through the graph convolution encoder, we quantize the features. And as I said, residual quantization module that extracts multiple features per face. So this means here in the image is like 6. You just flatten them out, pad them up with the start and end token, and then just predict the codebook indices. So this is like typical transformer training with just a new kind of vocabulary, have some sort of cross entropy loss at the end. And at inference time, you can now just start with a start token, and the transformer would just start predicting the next token. You sample it with some sort of strategy and keep predicting, right? So as we...
Sorry, for those wondering, there will be question and answer session for both Professor Niesner and Yowar before the end of the talk. So yeah, sorry.
Yeah. So what does this get out, right? Like Matthias showed a picture of like get 3D with decimation. So what we now get is like really nice compact flat surfaces, like 2 triangles representing the whole flat surface, really sharp edges, compact meshes. And this is without like doing any sort of post-processing, right? Like you're directly generating the mesh, you're not like generating a field and meshing it out. Okay. And we compare with all sorts of mesh generation approaches like AtlasNet, PSPNet, Polygen. Polygen was quite an inspiration here, like great work and kind of inspired us. And like we kind of outperform it in terms of quality and complexity. And yeah, here are some results on the tables in ShapeNet. Right. Yeah, I think it's a little bit slower. Yeah, anyways, like, so you can also, like, as Matthias said, like, what's really important here is to have shape novelty, because in a generative model, especially unconditional one, you just don't want to replicate your train set, right? Like, you want to have some sort of like novelty in the shapes you generate. And we do like a thorough analysis on that, and we can see that we can generate like some novel shapes. We can perform sorts of things like shape completion. You start with an incomplete shape, and then you, like, since it's a probabilistic model, you can just suggest different kinds of completions, right? Like, so it can start from what you give and suggest something new each time you sample. And like, one of the things that makes me most happy is like people have followed this up and like getting pretty excited about it. Like, we've seen multiple works like Mesh Excel, Pivot Mesh, Mesh Anything coming out like just yesterday. And I'm really excited that people are getting back into generating meshes again, like, and not scared off. So sort of like Polygen was an inspiration for us. Like, it's a like Mesh GPT is inspiration for others, and that makes me super happy. So yeah, that's basically about it. And I'll leave you with nice generation of all the meshes from our method on a room. And Matthias will take over from now.
Okay, so I think we made some good progress right now on mesh generation, but I think what big problem is right now, we still don't have textures, right? So we want to figure out if we want to use, I mean, this one is, you know, maybe there's an argument of scalability and stuff like this, but the question is if we want to use this ever in video games for content creation, we need to figure out a way to texture this stuff. And there was an easy way to do this. Well, easy way, we basically can leverage 2D priors, right? So you can go ahead and learn 2D generations and somehow figure out how to map this to 3D. So what we want to do is here, this is a project from Dave Chen. He graduated last year from my group. So he's done some really cool stuff on the texturing on top of the meshes now. So the idea is basically in this case, we want to get text input and the geometry, and we want to figure out how to map the textures on top of it. And so we started last year in ICCV with a very, very simple approach, actually. In this case, we have the geometry here given. You have a text prompt. And now what you do is you have a virtual camera, so to say, right? And what you do is you just take an image here, so you render it. And from this image, you actually can render the UV coordinates into screen space, right? So for every pixel right now, you basically know which pixel touched this part. And then what you can do is you can run a 2D diffusion model in order to generate an image, and you take the inputs or the generated outputs from the diffusion model and map it back to 3D. Now, the problem is not so easy because you actually also have to think about the geometry, right? So you need to have some condition that is aware of the respective underlying geometry. In this case, so we have the text, that's what I mentioned. And then what you need to do is you need to do some depth-aware inpainting. At the beginning, this is empty. We don't have anything given as a condition. So we basically just have the depth as condition for our 2D diffusion model. In this case, we run stable diffusion because that's, you know, I would say the only or the best competitor that is open source still at the moment for 2D diffusion models. So you generate an image in 2D, and then you have the texture given on the bottom right here. And based on the texture here at the bottom right, you can then figure out which texels map to which pixels respectively. Then you back project it to 3D. So you apply this texture. You have some part textured right now. You continue then. Now you have the next camera position. It's again a random sample. Based on this random sample, what you do is you render it again. You do again depth-aware inpainting. And now it's actually an inpainting process because some of the texels are already taken, right? So some texels were basically predicted from the previous pass, and you try to do a 2D inpainting. You make another prediction, you add it to the respective UV map, and then you apply it, right? And then you continue the sampling. So now you have a camera here on the top. Here you have a top view, you render it, have the same text input, depth-aware inpainting. This is what the diffusion model gives you, and you map it again to the texture, and at the end, you apply it again. And there's a lot of details actually here that what we have tried. So you have to basically make sure that there's no seams between the different predictions. And then you also need to make sure that you in a sense, you have to figure out which part of the 2D predictions you want to keep and which ones you don't want to keep. And the second part, what is really important, you have to make sure you select the right viewpoints, because you want to make sure that eventually everything should be seen, right? If you basically end up just with a bunch of random samples of camera positions and I have some texts that have never been seen, then you're missing a bunch of stuff here. Okay, but if you do this, for a single object, this is kind of tractable, right? Because for a single object, you basically can figure out around the hemisphere, around the bounding box of the object, you can figure out how to distribute cameras. And then you can get results that look something like this. Here's the geometry, text input is a compass, and here you see the baselines. This was clip mesh and latent paint, and here's our results that we're getting. Okay. A few more results. Again, here's the geometry given. Here we have clip mesh, latent paint, and ours. So we say we actually get pretty good results here. Same thing. We have a backpack here, geometry, baselines, and ours. Here we have a dumpster, geometry, baseline, and ours. Okay, so this was cool. But now the question is again, how do we go from objects to scenes? And this is like a theme that we have often in our research, right? You do the first works on object basis, and then you try to make sure how you can scale it to larger environments. And when I say scenes, I mostly mean like room scale indoor scenes. That means this is not a dumb research, right? Eventually you would like to do this for buildings, cities, and stuff like that. So how do we get there? Well, okay, so we have the geometry given right now for an entire scene. This is still relatively simplified, right? And this could be geometry from like 3D front or some similar data sets. You have now a prompt that says something like a Scandinavian style living room, and you want to figure out how to actually texture the whole thing. So now if you're running the same method that I've just shown you, this text to text, it actually has a bunch of issues. So the result looks something like this. So they're not that great. And the reason why they're not great is obviously you see more seam artifacts because you have a bit of a sampling problem, how you distribute cameras in a scene. The style is going to be also inconsistent because, you know, if you just do this iterative in-painting and never come back, it's kind of like a greedy assignment of textures. You eventually drift apart and you have a loop closure issue. Meaning that if you start on one side of a room and you just go around and come back to the previous one, your in-painting is not going to match up with what you had before, and you're going to get even more seams. And this is what you can see here in many places, actually. You see this on the floor a couple of times. And yeah, and then, you know, the larger the whole thing gets, the worse this becomes. And yeah, this is basically pretty difficult to apply to a whole scene as a single mesh. This is a very tricky problem. So we thought about how to make this better. And the answer is, instead of doing this greedy assignment with an iterative in-painting method, we thought maybe we can go ahead and formulate this more as an optimization problem in a sense of revisiting the areas that you already had. And this is a work that we're going to present this year at CVPR. It's called Scene Tech. So it's like high-quality texture synthesis for indoor scenes, and we use diffusion priors to do it too. So again, same setting, right? You have scene geometry as input, you have some sort of text prompt, and you want to texture it. Now, this one, as I said, is a little bit different. So here the idea now is we actually want to make use of score distillation, right? So we want to formulate it rather as an optimization problem instead of going iteratively and adding the stuff. To be more specific, we use variational score distillation because that's kind of the state of the art what everybody uses right now for all kind of various, dream fusion follow-ups in a sense. And the idea is basically, okay, you have here the latent features, you do score distillation here based on the text prompt, and then you back propagate respectively. So this is the definition of the loss here. Okay, we have the geometry then. And then what you do is you take, again, you sample random views. Then you have the UV map of this whole thing. You render it, so you get the UV embeddings. There's a bit of detail that I might skip here a little bit. There's a cross-attention between the texture encoders here. But then what you do is, based on this re-rendering, you're essentially getting gradients from the respective text prompts that you backpropagate in here. And the way you get those ones is you render this out as an RGB image, right? And based on this RGB image, you have this encoder here that gets you to these latent features. They are being fed into the variational score distillation. You backpropagate, and then you update the texture accordingly. And you iterate this one, right? So there's a lot of details right now that I'm skipping for the sake of time, but the high level thing, what's mainly different between previous methods is that this one essentially does score distillation similar to Dream Fusion, but instead of doing this in a nerf-based radiance field representation, you just do it based in the UV texture representation, right? It's actually pretty straightforward, and this is actually a little bit easier to optimize because you already have the geometry given and you don't have to optimize for the whole 3D structures. And this is why this won't look as, cartoonish or so what many score distillation methods are going to look like. And then from an optimization perspective, of course, you just continue iterating here, right? So you sample many views, and based on the view sampling, you're just getting gradients for the respective texels that have covered and touched this respective area. And then you have to make a decision where to sample the next views and so on. And this works actually remarkably well. So you're going to get results that look like these. And I think this is not too bad, right? These are the respective text prompt. You see the respective texture styles. And the thing what's important here, within a scenes, they are going to be consistent. So they're globally, they don't have any seams, of course, but they also have globally within the scene, they have the same style. And the way you get this consistency is you just iterate enough, right? It's a longer optimization. So basically, if you sometimes get gradients that are from a different style in one area, eventually, with this mechanism of the cross-attention and stuff like this, what we have, we make sure we enforce this is globally consistent. Here's another example. Again, we have a couple of text prompts here, and we're getting the respective results here that look like this. Okay, we have here a couple of comparison against latent paint, multi-view diffusion, and text stack. Okay, and we claim we look better because ours looks more consistent and overall the quality just is higher. Okay. A few more results, and so on. So now obviously you have seen now a couple of results here in this one for texturing where we have the geometry given. But now the question is, can we do both of these things at the same time? And yes, we can. And so what you can do is you can now basically go ahead and run MeshGPT first. So you generate a scene with a bunch of objects. Right, so this is what you see here. So MeshGPT is going to generate the geometry here. And afterwards you run scene tag on top of it. And you get the whole thing textured. And now this is an example basically where you have kind of full 3D scene generation with a mesh, with different types of textures. You have different prompts here. You get the geometry generated, and you get the textures at the end of the day. And this is where we are right now, roughly, with the research in our group. There's still a lot of problems we want to tackle, but I think overall we made, compared to the, generative models that existed before on like sun distance fields and stuff like this, I think we made quite some improvement, and we hope that this can be used for content creation pipelines eventually, but also for various scene understanding tasks in a sense. So big question is what's missing. So now comes some controversial stuff. So hopefully people are excited. So the obvious thing what is missing right now in all of these methods that use any diffusion and stuff like this as priors, it bakes the lighting in. So for any 3D content creation, this is a big issue. This is the same problem when you do nerve reconstruction, 3D Gaussian reconstruction, and whatever. We vision people, we are very excited about this, but the content creation people, they're not so excited about this. So there's not so many applications yet when you actually want to use this because it just bakes everything in. I need to be able to relight it. I need to decompose it with virtual assets. I need to have like virtual humans in it at some point and stuff like this. And this is still a big problem, right? So there has to be a lighting decomposition. There's some research on it, but I'm arguing this research is not enough yet to make sure that this works. But I think it's exciting. I think this is a very cool area. So we're of course not done. And this is an interesting thing to work on, I feel. The next thing was, of course, a big deal is scale and details, right? So these objects are fun, but these are not objects that you would use in a video game yet, right? If you're looking at like the latest, like blockbuster games from EA, Activision, stuff like this, they have a lot more triangles than that. So, and admittedly, this is a work from an academic lab, right? So we didn't scale this up to like crazy large models yet. If you're looking at the new language models that came out, like Llama 3 and stuff like this, that is open source, right? So, I mean, there's an obvious motivation how we could use these kind of things in order to get better, higher quality geometry with more details. And there's a lot of cool things. I don't know. Basically, all the things you can do for LLMs right now, I'm arguing you can apply here too. Especially larger context length and more detail, I think is critical. But also maybe augmenting it with 2D supervision might be also interesting, that you don't need only 3D data. And yeah, and then I have my last point, and this is maybe the controversial one I hinted to. The big question is, do we still need the 3D meshes to begin with, right? Because I mean, I'm giving here a talk among the top researchers on Earth, and there's a lot of debate in the last few years whether meshes is the right rendering primitive. And I want to convince you that yes, they are, but that doesn't mean that's the only thing we need. So obviously, our group also works on nerves and diffusion models and stuff like this. So we have a couple of different papers in different aspects. And I think the big question is basically, I want to make this comparison against with NeRF and 3D Gaussians. And I think there's still a bit of a confusion often for people who think, oh, we're just going to have everything to be a NeRF or a Gaussian, and then we don't need the meshes and the rendering primitives anymore. And if you're looking at the NeRF work, right, for instance, you might say, well, that's true, right? It looks pretty good. So it looks really amazing, right? You can do a lot of cool stuff with it. I already mentioned one problem that the lighting is baked in here, and it's very difficult to decompose. But there's another issue what you have basically. And the big issue is with any implicit representation, and I'm considering radiance fields also to be an implicit representation, right? Because it's a density and you have to kind of integrate it first. The big problem basically is, if you want to do rendering, you don't need all the stuff what NeRFs and Gaussians have. If I want to render, I want to basically have access to the surface, have an explicit representation, render it right away, have a rasterizer do it for me and make it fast. So this is going to be very efficient. However, if I want to do reconstruction or potentially generation in like a generative model, then you need gradients. And the problem is you don't know where the surface is yet. So you need gradients basically everywhere. And that's literally what a NeRF is doing, right? They use volumetric rendering. So my argument that I'm having here is if you want to do rendering, you want to have a mesh. If you want to do reconstruction, then you need to have some sort of implicit representation that defines gradients everywhere. And that's what NeRF is doing, right? So radiance fields are kind of on this edge, right? So if you take the original radiance fields, you basically have an MLP that stores a radiance field, you parameterize it this way, you optimize for the network weights. It's just a multi-view stereo reconstruction. And the argument here is you have gradients everywhere. So even if you don't know where the surface is yet, you're gonna get pretty good optimization results. That's the whole point of NeRF. And you can optimize with SGD marvelously because you have an MLP that over-parameterizes the space. And this is fantastic. So I'm arguing for any reconstruction task, this idea of volumetric rendering is going to stick. That's going to be a thing that will stick around in one flavor or another one. But if you want to do rendering, I'm arguing the whole volumetric rendering stuff is completely unnecessary. Like it takes a lot of overhead to do and deal with this kind of stuff. So you want to get rid of the stuff that is off the surface. You just want to have the surface once you converge in the optimization. And yeah, I mean, 3D Gaussians are kind of a compromise between the two, right? So you're kind of in the middle. You're kind of saying, okay, I'm going to have a bunch of gradients around the surface, but not everywhere. So I can do some optimization and I'm going to be much faster in rendering. But I know that everybody says, oh, Gaussians are real time right now. But you would be surprised how fast the GPU can rasterize triangles. I can rasterize on my 1080 ancient GPU. I can rasterize a couple of billion triangles a millisecond. That's like, Gaussians have too much overdraw. So you have to still find a way basically to go between these representations. And I think that the tricky thing right now in research is basically how to find a way eventually when you do reconstructions in any of these realms here and convert it back to a mesh. And so far for the past, 5-6 years, people have been relying on implicit representations, distance fields, occupancy, radiance fields, right? And it's very tricky to get back to this without running marching cubes. And I think there we need better ways to do that in order to actually make use of that content. With that, I think I'm at the end. I'm running almost a bit out of time. I would like to thank all the collaborators and all my students who have done this work, and hopefully we have time for 1 or 2 more questions. Thank you.
Thank you, Professor. If you have any questions for Professor Nisner or for you, please raise your hand. Please, there is no mic, so just speak loudly. And
Dr. Mr. Mark here. So you talked a lot at the beginning about how you started from LiDAR scans. You talked about these representations. Do we still need per frame depth estimation? Can you reconstruct it?
Yeah, that is a good question. So the question is basically, do we need depth data or not in the inputs? And I see depth data as a shortcut. So one option could be, so if I have multiple images, I can run a multi-view stereo reconstruction. That's basically what NeRF and Gaussians are doing. They are multi-view reconstruction methods that give you a 3D representation. So what depth data is doing, it's actually, so the Kinect is a structured light scanner that has a pattern you emit and you get it on a different camera. So they do kind of like, the multi-view is kind of this reprojection that you estimate in the pattern. So the big question is right now, where's the compute happen? Do you do it on a per frame basis or do you do it across all frames? And if you're looking at a phone, that makes it more interesting because on a phone, you're going to have a little bit of an optimization problem. What do you put in this thing in terms of sensors versus? So can I put in sensors that make my compute later easier? So I'm arguing if you want to do stuff faster for reconstruction, you want to have a depth sensor. That it's basically a compute compromise. So Yes, you can go and run forward network estimation, stuff like this with like Marigold depth and so on. These kind of things are cool, but they're not going to give you metric depth at the level of what you need for this. So I think whenever you have to do multi-view stereo reconstruction problems, it's just offsetting the compute, right? So this is, I think, the biggest tricky part here. And I would argue for some applications, you want to have depth. If you're taking autonomous driving, where you have a lot of, you have to be pretty fast. I think a LiDAR sensor is pretty useful there, right? You get an environment reconstructed kind of instantly. Whereas like if you had to run first like a Gaussian or a NERF, you see there's like 2 or 3 orders of magnitude in compute between to get a good enough surface representation. So I think it depends on the application, what you want to go for. I think there's definitely a lot of room for depth in LiDAR sensors, but maybe there's other applications where you don't need it anymore. And like if you go 10 years back, I think everything basically needed depth to do anything useful. Now with like learning methods, matching methods, NERF-based reconstructions and so on, you actually can get pretty far with multi-view alone.
One more question. Sorry, we're running out of time. We'll have a panel discussion at 5, so you can have, if you have more questions, you can have 5. One more question? Yes.
So you mentioned 3D world modeling, kind of, right? So with models like Sora, it seems like they understand 3D implicitly. So do you think like explicit 3D supervision would assist them, or do you think they're like solving a different problem than that?
Right. So since I was prepared about this, I have a slide about this. So of course, I think this is a fantastic question. So how do meshes and 3D data, how do they be part of a game where you do have video diffusion models? Like, do we need this whole stuff or do we just render everything alone? And I think diffusion models are fantastic. And I think they will play a significant role in the, image generation, video generation for all kinds of applications from entertainment and so on. And I think there's one big thing we have to consider here. So if you're talking about textured meshes versus diffusion models, I think it's all about control. Text is actually horrible control. If anybody wanted to actually do something and just generate a meme you want to put on Twitter, text is great. If you want to make like a movie and place a camera at a specific position, have a character animate in a certain way, text is horrible. That's just not the right way to control it. So the big thing is, how do we combine these two things? I'm not saying the video diffusion is bad. I'm saying the big question is, video diffusion has to be conditioned on some sort of like, better control. And I'm arguing 3D is the way to control it, right? You could imagine like video diffusion being kind of like a neural renderer. And then you can condition it on some sort of 3D structures. These structures could be very loose. They could be just a bunch of 3D boxes you're moving around. Maybe they could be extremely loose. And then the big question is, do we want to have more workload on the diffusion part and have like, very coarse boxes maybe just for the scene description, or do we want to have better 3D scenes for it? So I think this is an interesting question how this is going to pan out. And of course, I mean, rendering, training efficiency, diffusion models are not great at it. I think still the way to go for is have some sort of better 3D condition on the diffusion models. Whatever that's going to be, right? It could be more detailed, less detailed, and stuff like this. But one thing also, again, here to memorize everything here is very application dependent, I think. Right? It really depends. If you want to have a real-time game, having video diffusion models right now, that's probably not going to work. If you might have a movie and you want to do certain styles and documentation and stuff like this, how stuff's going to look like, I think video diffusion models are definitely going to come for this. This is going to be super exciting. I think there's a lot of cool research going to go around this one, how to use this properly. But I think, again, the main thing here is control. And text, I think, is not enough for many applications, at least. Yeah. Thanks.
Thank you, Professor. Some people say for
He is a resident of Microsoft Young Fellowship, Hong PhD Fellowship, IC Young Research Award, and many more. Let's welcome Professor Siegel.
Okay, that's good. Yeah. Yeah, thank you. Okay, so it's my great honor to be here. I'm Sui, and from Nanyang Technological University, Singapore. So today I will share some of recent works on these 3D children models. So our group started a project called 3Dtopia. So trying to build an ecosystem for all these 3D children models. So I think this workshop is all about this learning 3D from multi-view supervision. So there's two ends, right? At one end, we have the reconstruction. So sometimes have very dense views and sparse views, even single view. And on the other hand, we have the generation, right? Just like like Matthias has just introduced, we need controls. We have like text controls, image controls, other different 3D controls out there. So actually in the past 2 or 3 years, we have a great advances on all these different fields. And today I want to talk about the 3D gen models. So I think 3D gen models have like 2 tracks nowadays on the top conferences, right? On the one track, it's working on these limited categories. So we also have one works called DeepTF, and also the very good Mesh GPT has just introduced. So actually people have explored different 3D representations like points, mesh, 3D Gaussian, triplet, voxels, but still looking for very good representations that can achieve a strict balance between the efficiency and also the capability to model a complex 3D world. And on the other hand, it's on this general object that is trying to learn from the massive 3D data in the world and to learn really generalized models. Nowadays, of course, OpenAI have the pointy, shapy, then Adobe have the instance 3D. They use the large recognition models. And we also trying to extend that to LGM, and also NVIDIA has the lattice 3D nowadays. I think they all have very great progress, and one important lesson is the 3D representation is really application dependent. And for any other field, we have to build ecosystem to run, right? So especially in computer vision, we not need models, we also need data and also the evaluation protocols. So nowadays, I will talking about all 3 of them, that we're trying to build in the data set, the models, and also the evaluation benchmarks for the 3D general models. And here's the overview. First, talking about the object data set to build, and also 3D and 4D. So I think some people have asked about the Sora, right? So here I want to combine the 3D general models with the video priors to enable 4D generations. And finally, I talk about some of the stuff on 3D generation evaluation. So all the general models, they're pretty hard to evaluate, just like the large language models, right? So in language model, we have the arenas, or we have a bunch of benchmarks. But in 3D, we only have very limited metrics, something like flip, FID, something like that, with definitely better ways to do the evaluation. Okay, so first I will talk about the 3D object data set. So I think last year we have built this OmniObject 3D. So compared to the Objectverse everyone is using, so this one is a real scan data set. We also have very good quality controls to ensure every object inside should have a very good qualities. So we support different tasks. Here compared to like the synthetic data set, like the shape nets, or the multi-view images, the code 3D, or the MV image nets, and also some of the real-world 3D scans, like also the Google Scan Object, GSO is also widely used nowadays. So compared to them, we try to achieve first large categories that we support 200 daily categories of the 3D objects, and also the high qualities. So we use very professional scanners to scan 3D objects, and we also ensure it's all from the real world. That is all the object inside, that is from your real life, right? What we are seeing in your daily life, we have included in our data set. And here is kind of statistics at that time. We have like 200 categories out there. We have 6K objects, and we include a lot of different annotations, like the mesh, like the textures, like the multi-view images, like the kind of scan videos. So we're still collecting more data. So the size of OmniObject 3D is still growing. So I think new version with more like 18K 3D object will get released very soon. And now we are actually supporting 4 different tasks. The first is perception. So still a lot of people trying to develop new architecture for 3D perceptions, right? So now besides the point net, point transformers, and now people are also using like different different architectures for the robust and accurate perception. So we can support that to more categories. Another thing is about the service reconstructions. So we want to ensure our results not just look good, it still can enable a lot of real-time applications. So you should have very good geometries that is on the service reconstruction. The third is multi-view, this orthogonal view synthesis on the nerve, 3D Gaussians you can use in our dataset. And finally is about the generations, right? So for this part, I think that is I'm focusing on more in this talk. And now we are also building this object V2. So besides these different objects, we are trying to include two different modes, orientations. The first is about the text, very fine-grained text. So one lesson we're learning from Darley with Sora is that very fine-grained text annotation is very important for learning a very good generative models, especially for 3D, right? So we're including fine-grained text. Another is on this 3D pose. So in a lot of this data set where people working on 3D generative models, some people just assume we have these canonical views. But we know like which view is like should training the data set on. However, in the real world, we don't know, right? So we should have to be able to predict the safety pose. So that is the two things we have included. So first, I think I want to show some of the new annotations. So for each of the object inside data sets, we have annotated 5 different aspects. The first is memory, like it's a pickup. The second is the appearance, very fine-grained description of the appearance, like this, a relative small pickup with kind of brownish red exterior and white interior, right? So you have very fine-grained appearance for both the exterior and interior, and also featuring blue line pattern as top, right? So we have all these fine-grained annotations, and also the material, so reflective, smooth surface, spell, simplicity, and function is for author storage, right? So you can use this kind of annotations to enable a lot of different stuffs out there. Sure.
It happens randomly every hour.
Okay,
So
yeah, sure, yeah. We can, okay, it's working now. That's good, that's good, yeah. And
breaks the rhythm.
okay, yeah. And for this post estimation, we are also building kind of Omni60 data set built upon our objects really. So you have all these 200 different categories. And these categories, they are placing all around these different things. Some of these indoor things on the table, on the floor, they have different shape pliers. So now a lot of people working on 60 posts, they are working on single categories, or they have some templates. So here we want to go for generalized track. That is, you can predict the 60 posts for any of the objects, right? So after that, I would like to talk about the 3D generative models, right? So I assume you have already seen lots of them. So here we want to introduce one of our recent efforts. It's called 3D Copia. So we know that there's 2 tracks or 2 methods to tackle 3D generative models. The first is 3D native. That is, you just learn from the 3D data. You just try to learn the mapping between text to 3D or image to 3D. Another type of methods, they just leverage 2D prior, like diffusion prior in stable diffusion. They use the score distillation, SDS, to do this. So the 2 different methods have their own pros and cons. So for the native, like the 3D methods, so they have very fast sampling speed, right? You can do this generation within a few seconds. However, most of the time it has the lower generation quality compared to the SDS-based method. And on the other hand, the SDS-based method has very high generation quality, but it's pretty low. So usually it's a few hours, but nowadays people have been speed up to like 10 minutes, something like that. So in this work, we try to combine these 2. That is, we propose this hybrid diffusion prior. So we have 2 stages. So in the first stage, we learn very straightforward 3D diffusion models that can generate coarse 3D shape and texture within just 30 seconds. Then with 2 additional minutes, you can refining all the textures using this SDS. So when I talk about for the SDS, we have 2 different aspects, both on the kind of points and also on the latents. So it can ensure very fast sampling speed, just 3 minutes. and also pretty high generation quality. So I think since we are aiming for foundation models, so we have also combining large-scale data sets comprises of like Object XL, our own data sets, and all of these open source data sets out there. So we have done this different model view, image rendering, and this 3D captioning is pretty important. So previously on the OmniOps 3D, we have the fine-grained annotations. So that is manually edited. It's very hard to scale into like millions of 3D objects. So here we combine Lava, LavaNext, Vicuna, GPT. We find a very, I think, automatic way to get high quality 3D captions for any of these 3D objects. And we do some cleanings to filter out the objects that is not suitable for the fitting. And finally, we in this work we choose the triplane, right? Triplane to be the as the 3D representation. So I think here is very straightforward way. You can just think of the 3D counterpart of stable diffusion. We also leverage the latent diffusion models. We're just operating on this triplane VAE. I think this is very important. So it's kind of bounded the performance or bounded the rendering, final rendering quality of the 3D models. So I think in the video generation it's the same. That is, some people training the video VAE, right? So the VAE is actually your outbound for the generation. So we also spend a lot of time to tune the VAE, these autoencoders out there. So in the second stage, we have, of course, we want to get to mesh, right? That is, can be deployable in the real world. So in this work, I think it's pretty simple, multitude plus some post-processing. So we have two refinements. The first is on the latent space, another is on the pixel space. So these two, they have their own advantage. So latent space, they can fix some structural artifacts. And for the pixel level refinement, you can get you very good textures out there. And here is the comparisons of our 3Topia to like pointy, shapy. I think you can see some results like Hamburg and the Arctic Fox. So we can get pretty good results within like three minutes. So here is some demo videos. So you can use that to generate a bunch of objects with high quality mesh and textures out there. It's also highly diverse because we train on millions of 3D objects. But here we're trying to fill in a museum using all the 3D objects that we generate. It's a cargo ship. That's what we can do is trying to build an office, right? Headphone, handsets, lamp, sofa, coffee table, mug, sushi out there, hamburger. And you can also build in your own like spaceship on the moon. Okay, so that's our kind of first work. We're trying to go in the full cycle of the data, the annotations, the kind of captioning, the 3D models, the VAE, the diffusion models, and more. However, this kind of generalized 3D models is not enough for the real world applications, right? Especially in the game design. So in the game design, people want customized assets instead of generalized assets, right? So you actually want something like very look like the buildings here or like the models here, right? You not just want some random like buildings out there. Just like I would like this Chinese style, these buildings. However, it's very hard to describe using text, right? So here we propose this sim station, so using SIGGRAPH this year. So we want to generate 3D assets from just a few 3D exemplars. So you can have your own like 3D artist. They create a few 3D5 these objects. Then we can generate more, have different variations, but also follow your style. It's customized 3D assets. So I think the overview of the framework is also straightforward. So in this work, we are focusing on the quality. So we still choose the score distillation. We propose this dual score distillation out there. Since we have reference models, right? We want to follow the style of the reference models. So we have this reference trial, and we also have this concept trial. So here we also try to leverage the power of stable diffusion. So you can think of this scene-driven diffusion as a LoRa version on the 3D, on the multi-view. So we try to train some of the LoRa's on this kind of reference models, then generates the 3D assets that just customized to your need. And here's the results, right? So just given 5 or 6 different models, reference model out there, you can fill in like the same style building with different variations, different heights, also different styles out there. And for the following one, we're just trying to build a game. The game out there, you can generate these 3D galleries out there. And here is the more results. You can see the geometries. I think it's pretty good. And it's didn't look like the reference. Even though the style is the same, you can see some of the reference on the clock at the certain. So after that, of course, it's still not enough for the real world applications because we want to put these 3D objects inside a certain thing. So we need 2 things. The first is we need the modeling of the material so that we can do some relighting, reflectance, right? Another thing is that we also need some editing. Sometimes we don't just content with what we have, won't change the color, won't change the style, right? So can we have some 3D driven models that can also be re-renderable and also editable? So that is the hypertuner. So we want to do 3 things. The first is texture resolution. So it should be hypertension enough. The second is the material modeling. The third is some interactive texture editing. So I think the key idea is to leverage all the priors we have. So of course we have this 2D division prior. We also have the semantic prior, like the SAM models nowadays. We also have some of the models they just doing this material prior, like the de-rendering. Of course, nowadays we can also use the large language model or this large multimodal models out there. So the general idea, I think due to the time, I will just quickly go through. So essentially we have this diffusion prior and also other priors on the material so that we have the loss function for this albedo, for the segmentations, so that our final results, you have all the parts, the semantic part. So you know which one's the head, which one's the body. You also have the specular albedos so that you can do this material and relight it, right? Essentially, we leverage a lot of these pre-trained models, leverage the power. And during this interactive editing, we actually enable this one-click editing. So that is, we have some positive prompts. So I want to edit in this part, and we also have some negative point prompt. So that is also echoes what Lucille has just pointed out. That is for the 3D generation, we not just need text, we need more ways to do the control. So here's the demos. So you can see it's a very high quality. It's also have the materials out there. We can have our HDR map, we can do the relightings, and put the 3D objects in different environments. We can also do this animation. And finally, this interactive editing. You can choose one point and you can select the region and also describe what you want. You can have different style, dental style, you can have different things like the clothing part, different colors. And for the same case, you have all the other options on there, right? So that is the hypertrimmer. And regarding the material, we find it's pretty important for real-world usage. Have good, like the geometry knowledge, especially if you use the mesh, right? If you have a mesh, then how you can get a very good, reliable material? In the previous hypertrimmer, we use material prior from previous work. So in this new work, we find that the current large multimodal models, they are powerful enough. That is, we can distill knowledge from the large language models to help our 3D people to do this material modeling, right? So the motivation is that we can leverage these multimodal large language models to provide the priors for this yield loss problem. Because given you a 3D object, it's very hard to do this disentanglements and also to classify what is the material is. I think the method itself is straightforward enough. Of course, we first do the rendering and segment different parts, and we use this kind of GPT-4 to build the material library and use it to classify each of the part into certain type of the materials. It's called the MM-based table. And we use this retrieval to get the materials like this metal, this marble, to try to fuse them to do the final material generations out there. That's the final results. You can see nothing fancy. So we just try to convey an idea that is the current large language model already knows a lot of this reading, right? You can definitely leverage that knowledge inside. So here is the demos. So it's before and after. So we have all the materials inside. So given one of the original 3 objects, then we can do this make review that's given the very map. When do all the rewriting, the material kind of model is out there. Okay, so the time limit, I will just stop here for this work. So after that, we are thinking about like what's next, right? So previous work we need like several minutes or even hours to complete. For even though we have very good textures, very good geometries, lighting, the editing. However, nowadays people actually want very high generation speed. So that is, can we just generate something within a few seconds, right? So that is, we try to bring the Gaussians into the speed generation. It's a field Gaussian, so this here, unclear, generated Gaussian statics. So essentially, I think the key idea are twofold. The first is, of course, replace the nerve with Gaussians. Of course, we have to think about how we design Gaussians. The second is, of course, we need a very highly match and texture. So we do this dismantlements. So we have this diffusion, mesh, extraction, and also this UV space, this texture refinement, right? So 3D recognition matters, right? So Gaussian splatting, it grows from small number of Gaussians, but it doesn't have a very good like the service of the mesh. So mesh is hard to optimize from scratch, but it's very good. Second stage, right? So of course we leverage the advantage of these two. In the first stage, we want to get our gradients as fast as possible and get a very good cross shape. So we use the Gaussians. On the second stage, we switch to mesh and the UV space textures out there. So you can see we have these demos, so we can generate pretty fast, right? So we start actually from a small number of Gaussians. And so the shape can be very fast. And during training, we add more Gaussians. So you can see it's kind of real-time demo on it. You have just wait for like 30 seconds, you get pretty good results. And for this UV space texture, I think I will skip that. Of course, we also leverage the score distillation and also this SD edits, a lot of these image editing models, 2D methods to help with the enhancement. So here are some of the results for the text 3D, right? So the different stage, it took 2 minutes to convert to the final, to the final results.
Somebody close them.
Oh.
Sorry for that.
Yeah, that's okay. Yeah, that's good. Oh. Yeah. So and we also have this image 3D results. It's just take like 1 minute to like converge. But still have some problem, like the back view is blurry compared to the front view. So we want to also tackle with that. So that's our new work. It's called LGM. It's a large Gaussian model for high resolution 3D content generations. So the first contribution is that we kind of boost the resolution of the 3D generation from like a lot of people working on 256 by 256. We boost to 512 to 512. It also only needs seconds of time for this generation. The key idea still follows the direct regression. So we're first using multiple generation models like ImageDream or ImageDream, something like. You have this 4 views, 6 views of that. Then you just put all the multiple image to this large Gaussian models. So for this part, you only need 1 second to get this final Gaussian out. And convert the Gaussian to the hybrid mesh, we take another 1 minute. So here's the results. So at the time we choose between the UNAPs and also detention and transformers. We find that UNet is simple enough. It's also very lightweight, so we can scale in the resolution to 512. And we use a very simplified method, just this cross-view self-detention. So we also don't propose like very new operations to just show that using these multiple images and all this camera array embedded is very important to build into your UNets. It's a very shallow UNets. With just this cross-view self-detention, you get a very good Gaussians. And for the mesh, we have some methods that is, we try to combine this hash rate with mesh. So it's better than the previous, like Topia, we just use the machine group. So for this one, we found a better way to convert Gaussians to good mesh so that you can use in these graphic engines. So here are the results. We also show the Gaussian points of the image to 3D. And also this text to 3D. So you can actually get the results within 5 or 10 seconds. So you can also try online. So we have online demos. You can input your own text, your own image. You can get the results. So after that, the kind of the Sora came out, we also think about, can we also leverage the video priors to enable not just a static 3D content generation, but also dynamic generations. So the first work is called like DG4D, that is the Dream Gaussian 4D. So the basic idea is that we leverage both 3D priors, these 3D native priors, and also the video priors. That is something like if you have the Sora, so here we're just using the SVD, the stable video diffusions for these high quality 4D generations. So the whole 4D generation process can also be resolved within 5 minutes. So it's a huge improvement from previous works. So some of the previous works they need like 5 hours, right? So here you can see you can generate an Anya within 5 seconds. So here is our pipeline. The basic idea is we try to do this SPS, the score distillation on the video data models. And you have also want to refine the textures, just like the previous in the Dream Gaussian. But here, the UV map is on the temporal, right? So you want to use this UV map refinements also according to your temporal movements and also temporal trajectories to get the final results. And for this part, I think I may want to speak. So if you want to push the Gaussians from 3D to 4D, you also want to enable the temporal modeling. So here we have a hexagon. So we have both the space and time. So initialization is very important. So we also use these residuals so that at the initial points, your Gaussians are different. Then they try to model temporal things out there, right? So initialization is static 3D Gaussians, dynamic is a hexagon, and finally is the video priors. So you can a very powerful video prior can generate a realistic 4D content out there. So I think here is the results for the, maybe I will just yell, okay? For the pandas out there and also for the flag, right? You can see it can learn the different video priors from these training models, right? Not just for the humans, for the animals, you also have very generalized dynamics out there. So it can doing all the things within just 5 minutes. Okay, that's good, that's good. But we're still not satisfied with results. So that is our more recent work. It's called L4GN. So that is we try to extend our LGN, large Gaussian models to 4D space. So this work is a collaboration with NVIDIA. And it's called large 4D Gaussian differential models. So the idea is pretty simple. That is, we learn a feed-forward network that is given a molecular video. We can generate a sequence of 3D Gaussians within seconds, within 2 seconds, right? So you can also opt even on the Sora videos. You can give an MU or Sora videos. You can get 40 versions, right? If you want to know like what's behind this author, we can do that. Of course, first we curate the dataset. It's called Objectverse 4D. So we try to select all these animated objects in this Objectverse, and we filter out the motions not obvious or very strange objects. This finally resulting like the 300 million images for the animation. So I think you can see so the pipeline is pretty similar to the LGN, right? We also use the UNets We use the LGM pre-train. So besides that, you can see the input is actually molecular video plus this smart video generated by the image stream or like the image stream, something like that. And finally, you can have the Gaussian sequence. So the good thing that we finally have the first feed-forward network for 4D generation. So first 4D generation, they are using STS, score distillation, optimization based. And this feed-forward network is very simple. You just have one UNet, and you can also complete all the inference within a few seconds. So here's the results. We can also do this autoregressive reconstruction of long videos. So here is the Sora video. We can run the video. I think this lasts for 10 seconds. And at the last row is our 4D reconstruction results. And we also develop interpolation models, right? So sometimes the 4D content seems quite jerky. So if the movement is pretty large, we want to interpolate these in-between Gaussians. So we also learn these 4D interpolation models. So our final 4D contents have enough frame rate to view on this different platform. And here is comparisons. You can see these are another Sora videos. We can do this 4D reconstruction within just 7 seconds. Compared to our previous work, Dream Gaussian 4D is 10 minutes. But because this work is feed-forward network. Okay, let's go to our final part. That is, we show all these fancy results, but how do you compare different 3D generated models, right? So nowadays, like you can see on Twitter, like every day there's different 3D models coming out. So how do you compare them? So our first guess is that maybe, okay, we can leverage the kind of GPT, right? So first we use the GPT to do this material modeling. So here we find that it's also very good evaluators for text to 3D generation. This also will be presented in CPR. It's called GPT-4V. It's a human-aligned evaluator for text to 3D generations. So we have a very rapid progress in the field, but the evaluation matching has lagged behind. Right? So one way to do is just using the GPT-4V. So here we provide a very comprehensive prompts suite, and also a way to compare different 3D assets. So here we just show some of the pipelines. So for here is the different subject we have covering: living beings, plants, buildings, vehicles, households, atoms, closets, right? Anything you can think of. And also try to compare the appearance, geometry, like the scenes, the styles out there. Of course, if you want to make good use of the GPT-4V, you have to write good prompts, right? So here we also show you how to make the prompts. So first is the image prompt. We find that GPT-4V can do quite well on these multiple images. You just have to concat all these multiple images together and fit into the GPT-4V as a single image. And then you want the GPT-4V to compare left and right on different aspects. So we also, you can see the captions. The caption already good, and when you do the comparisons, it can get the scores. So you can see here is one of the outputs of the GPT-4. So you can see the right model shows something that is without the kind of the tangible object needs. And the 3D possibility appears distorted and blended with something, right? And for the texture details, it's more blurred and less sharpness. It's already like compare quite good to the left and right the generation results. So the final answer for the 5 different aspects, 5 different dimensions are GPT-4 things the left one, then right. So you can get all these comparisons of left and right, and how to combining the scores together so that we can have a benchmark or rankings of 3D generated models. So that is we borrow from the LLM, right? In large language models, they have the LLM arenas. They use these Elo scores. So we also doing the same thing. The comparison is noisy. A is better than B, A is better than C, something like that. So we try to aggregate all the different LS comparisons. So finally, we also try to evaluate how this GPT-4 to our human perceptions, right? So also collect a lot of this human perception data. We find that the alignment is pretty good on all the 5 different dimensions, right? So our metrics actually reach top 2 alignments in all the, here is the 6 on including average. criteria out there. So we can actually achieve automatic evaluations just using the GPT. And finally, we also building, we try to build another arena. We find that the human presence data is actually the most valuable, right? It's most reliable things. So we trying to combining like two tracks, text is 3D and image is 3D. We have like 10K gen models. So you can play online. So it's called 3D gen arenas. So you can contribute to all data point so that we know like which 3D gen model is better. So we have included like the point-based method, Gaussian-based method, nerve-based method, also maybe mesh-based methods inside it, right? So they can have the comparisons across all the different dimensions. So you can feel free to try it out. Yeah. Okay, so I think that's all for my talk. And thank you. I'm happy to take any questions.
Thank you. Thank you. Thank you, Professor.
Thank you, Professor, for the talk. We have actually 8 to 7 minutes of question and answer. So please feel free to ask Professor Julie any question. Just raise your hand and speak loudly, please.
Have you tried doing all of this is object centric, right?
Mhm.
How easy is it to extend this to scenes?
Yeah, we have a lot of work on things. We actually working on both indoor things and outdoor things. Recently, we're working on cities. I have a work called City Dreamer. So I have another talk this afternoon in the kind of content generation workshop. You can go there and we'll introduce our work on the scene generations.
I have a question for the 3D software data.
Yeah.
So when you feed the tracking, will you describe the data post aligned or not?
Yeah, I think that's a pretty good question. So we find that if we have the post line, like the data, it will help with the fitting. If we don't have that, it's also okay. Yeah, it's noisy, it's kind of converts slower, but it will not influence the convergence. Yeah. Right. Thank you.
Any more questions?
And if you have a balcony, how convert this
Yeah, thank you for the question. So we can go back to this part. So actually, when the GPT compile two different models to output some text, we are also trying to output the decisions, which one is better. So you can see the final answer is left, right, right, right. So it tries to decide. So on this dimension, on the geometry, maybe the left one is better, and on the textures, maybe the right one is better. So I think that's another advantage of using the GPT. We also got some sense of this interpretability. So you know why it is better or why it is worse. You will try to elaborate, like something like the less ingredient of the fish, right? You'll try to explain why the GPT will try to explain why the thing is worse.
Try to experimental mix I think I think directly predict the GP, not the experimental mix. So it actually lacks the variant view. So I'm wondering if they ever try to use the directly predict the spherical harmonics.
Yeah, I think that's a great question. So actually in the LGM, we try to follow this direct regression ways, also this LGM. We haven't tried that, but I think that's a very interesting way to do, and it's just predict the high harmonics. Yeah. Yeah. Okay, so I think you may need some tweaks of the representations. If you switch from this RGB to this harmonics, you have to choose the right way, like the distributions. You don't want the range to be too large, and also the learning rate is a lot of things to tune. Yeah. Yeah. Thank you.
Thank you. I think like in Photoshop now they use activating edit images, and I'm wondering regarding 3D editing, if you think like the technology you're developing will be soon mature enough to be like in software like Blender to help artists do 3D editing with maybe prompts or like on the spectrum of the evolution, how mature is the technology?
Yeah, I think for now, that's a very good question. But for the simple categories like the tables, like some of the boxes, like the kind of the bottles, they are ready enough. We call it predictive geometry textures. So some of our work have these Blender add-ons. So you can actually use that add-on inside Blender to do the editing and generations. But for more generalized kind of objects generation editing, still need like I think 1 or 2 years. So the Adobe also work on this. Yeah. Thank you.
When we train a 3D model using diffusion projects, we sometimes encounter Janus problem. So have you ever met that problem and how to resolve that issue?
Yeah. So I think when we're training like the 3Topia, these large models, right, across different data, I think the data cleaning is pretty important. Yeah. So that's sometimes what we find that earlier we solve something with, inside the model with code, but when we're doing the debugging, we find that's actually the data. So I think the architecture itself is already very standard. We have the diffusion, latent diffusion. You just choose the good 3D representations. And if you encounter like some of the problem during the training, most of the time for us is from the data itself, like how to do the pose, like how to dealing with some of the white textures. So it will influence your gradients so that you can get a very good training dynamics. Yeah, thank you.
I have 2 questions.
Okay.
So, thank you for the talk. The first question is regarding the GPT-4. So GPT-4 is a closed system. It can change every day, right? So for evaluation, we need something that's standard, that will not change over time. So what do you think of that aspect? Should you use like a lava with like recent, like why specifically GPT-4?
Yeah, so I think that's a great question. So when we're doing this GPT-4, we also worry that it's a closed source model. It's also like updating like months, something like that. So if we are like evaluating this month and next month, it's maybe not so consistent. So I think I have 2 thoughts. The first is that we have compiled open source models on this task. It's not so good. We have compiled like Lava Next, and also a lot of models have learned like some of the models from also Stanford, they are not close to this GPT-4. So GPT-4 still wins in this 3D perception, right? So we can't, for now, we can't use the open source model to replace GPT-4 for evaluation. And the second thought is that we have compared different like versions of GPT-4, like from like January, like to the March, something like that. We find that they are consistent respect to the ranking. So even though the score, they're not consistent, but the ranking is consistent. So I think in the future, I also expect large, like multimodal models, they can have a very good progress, so we can use the open source models.
Thank you. My second question is regarding the LGM work. So you rely on MB3 to generate multi-view. And that paper is trained on Omniverse, and also you trained on Omniverse. So does that limit the generation capability? I mean, many of the people have noticed if you try like things outside of the Omniverse distribution, it basically fails. But in our scientific point of view paper, try to combine like both, like something that's trying to rely on like stable diffusion and something that's trying to Omniverse. And we found like there is a trade-off on. But how do you see like if you only want to train on these 3D data sets or fine-tune these 3D data sets, how do you not lose? Forget like the pre-training and basically not overfit to the distribution of the operators?
Yeah, that's a great question. So actually, I think like Match is actually a very wonderful work. So for this LGM or L4GM, so both of these MV3, these multi-generations, and also the final discussion multi-Gaussians that trained on observers, we find that the second part, that is the LGM part, they are quite generalizable. So most of the errors or most of these kind of limitations come first, that is the MV3. So if you have some like OD inputs, you will not get very good these multiple images. I think in the future we should like train this from the smart view diffusions using different data sources, like the Lion 5 billion, like the 3D native data, even for the video data, we should leverage them to train a very robust and generalizable multivariate diffusions.
But do you think like this second part that we train, can it somehow in the future be able to correct any errors from the first part of the pipeline? So let's say my multi-view diffusion generated a bunch of images. Some of them are inconsistent. Can the second part somehow correct that?
Yeah, that's also a good question. We're working on that. So for this kind of LGM, well, for GM, if we incorporate some uncertainty modeling, that is, we know like which view we should trust and which view is not so good, has some artifacts, then we can somehow correct. Yeah. Okay, thank you. Yeah.
Thanks. All right. Okay. You store let me see if I can get rid of this thing. Okay. Yeah, so we think about these representations like instant NGP. I'm sure most people in this room are familiar with it. You know, at every point in space, you store an occupancy and a color. So abstractly, we can think about it as four numbers. And oftentimes it's stored in a hierarchical representation. So we have coarse scale colors and fine scale colors. And so the simple observation that we made is that when you want to sample a big volume as part of the cone, just sample from your coarse scale nerf. So the kind of interesting thing about this perspective is that a lot of these voxel representations were already training coarse models and fine models. So all we had to do was really uncomment a few lines from a piece of code, and now you can get this modeling of essentially anti-alias kind of reasoning, where you can integrate big pieces of the world to help project what you expect to see at a pixel. Yeah, so the simple answer is we have coarse voxels, and when we want to sample this big volume, this big piece of this cone, we just sample, we query the coarse nerf, and when we want to sample this the small piece of this cone, we sample the fine nerf, and then we at some level still just do 1D sampling. So the take-home message here is that it's really not any slower than what you would normally do with a nerf, but you kind of get anti-aliasing for free. I should still say it's not as high quality as ZipNerf, but it's quite fast. And this is integrated in Nerf Studio, so you should give it a try. And I think that the lesson here is that I think a lot of the reconstruction tasks that we're doing in the volumetric world is ultimately we're trying to reconstruct in some sense a continuous function, a density field and a color field, a radiance field. And so one intuition I would have is that we kind of know, if we open up our signal processing textbooks, rules about how we should do frequency modeling and Nyquist rates. How do we sample, how do we reconstruct continuous functions? So essentially, I think about this as like a low frequency versus high frequency approach to reconstructing this continuous function. Okay, and I'll just throw one more kind of quick kind of comment on scaling this to high resolution. So the other interesting argument that I'm making, I think, about building large-scale nerfs is that even though I sort of emphasize we're trying to do it across large spatial footprints like city-scale reconstructions, at some level, nerf doesn't really care about absolute scale. It doesn't know if you're trying to reconstruct a city or a little toy model of a city. So the real question about scale deals with the number of pixels that are at play. And the quality of the resolution you're trying to, the kind of the fineness of the reconstructions you're trying to build. So in the context of virtual reality, we've also looked at projects on, how do we build kind of very accurate but fast reconstructions that enable interactive rendering. And one of the insights here, this is a paper that Haifeng will present in a couple of days, is that it has to do with nerfs and occupancy modeling versus more surface representations. So the starting point is that even though nerf really is a volumetric model of the world, if we look around the scene that we're in now, most of the world is empty space and it's hard surfaces. And so we know that kind of surface-based models tend to be a bit more efficient. And a very popular one that uses the backend for nerfs are signed distance functions. So for example, if I stored a signed distance function representation of this world, it's much more efficient to sample because when I throw out array, there's only, I can actually evaluate a signed distance at some sample. And if it tells me the closest surface is 50 meters away, I know I can jump 50 meters before I intersect any other surface, because that's what a signed distance function means. So it turns out it's much more, this is called sphere tracing. So it turns out it's very efficient. There's much more efficient algorithms for reconstructing surfaces where you have far fewer samples. So the take-home message here is that most of the world that we look at is actually surfaces, but it turns out sometimes it's nice to model things volumetrically if you have really fine scale surfaces that it's hard to estimate precisely. So essentially, what Haitham did is came up with a representation, we called it a hybrid nerf, that models 95% of the world using signed distance functions and 5% actually using volumetric sampling. So this is a visual of normal volumetric sampling of when you throw out array, how many times you have to sample the array in order to get a high accurate reconstruction. And the take-home message was that by exploiting the fact that most of the world can be modeled with signed distance functions, you can get this sampling much more efficient. So where you need almost an order of magnitude fewer samples per array. So you kind of get the same accuracy of a full volumetric model for the efficiency of a surface model. And the insight is super simple. Actually, sorry, here. Sorry. There's something that, let me throw this in here. Okay, apologies. I missed a slide here. So let me just go back to. Okay, so the insight here is that the way a lot of these signed distance function backends work for NERF is that instead of learning an MLP that spits out a density at every XYZ point, it spits out a signed distance function. But then that signed distance function, oftentimes, so what that is a signed distance value. It's the distance to the closest surface, and it's positive for outside and negative for inside. And oftentimes that is converted to a density that is between 0 and 1 with a squashing function, something that looks like a sigmoid. And what's super crucial is there's a temperature parameter that tells you how much do you squash everything. And this temperature parameter beta is oftentimes set globally. So if this temperature is set really high, then basically you take your signed distance and you snap it to either 0 or 1 by pushing it through a squashing function. If you set the temperature really low, it's as if you're on the linear part of the sigmoid curve, and you get a lot of partial values. You get a density that's not 0 or 1, but it could be 0.5 or 0.7. And so the problem is that if you want to set this temperature parameter globally, if you set it too low, you get lots of samples. You basically treat the whole model like a volumetric one, but it becomes really expensive. If you set the temperature really high, it forces the final densities to be 0 or 1. And so the whole model behaves like a surface model, but then you end up doing really bad on thin structures like this pole here. It turns out this is where it helps to do volumetric sampling. And so the insight that Hytham had was actually, let's learn a spatially varying temperature parameter so that most of the world ends up using a lower temperature. Ends up using a higher temperature that allows the model to behave like a surface. But some points in the space, when you have skinny things or when you have partially translucent things, you actually have the model behave like a volumetric renderer. And then there's sort of tricks to say when you end up having a low beta, when you end up having a high beta, you can basically use tricks like sphere tracing to make it super efficient to render. Okay, so that was really the first slew of techniques on modeling, extending NERF reconstruction to large spatial reconstructions. And so now I wanted to get into what are some of the things we've been looking at to take these neural reconstructions and really make them work for a dynamic scene. And so here's some visuals that I'll show off here. All right. Okay. So at its heart, modeling a dynamic world is something that I think most people in this room probably have seen. At this point, it's fairly well studied. You still end up doing a forward model, but instead of hypothesizing a volumetric static world, you hypothesize deformations of that, some canonical volume. And so the perspective that I'm looking at is you are just given a video with no knowledge of where cameras are or what you're looking at. But if we take this forward rendering model, we hypothesize the canonical space, we hypothesize deformation, we hypothesize cameras, we press render, we get RGB pixels out. And now we can compare that with the actual RGB pixels and try to update our models, both in terms of our shape, our deformation, and our cameras. But this problem is horribly under constrained. And so why are we able to hope to do this? And I guess the key question we've been looking at for a few years now is how do we really exploit prior knowledge? At some level, this whole view of vision as inverse graphics, I think of as the anti-big data story. It's just sort of taking the pixels that are in front of you and trying to fit to it. And we know that if there's ambiguity in the fits and there's sort of impoverished views, at some level, we should really bring to bear all the prior knowledge about how other rooms I've seen and other cats I've seen and other people I've seen, that helps me really fill in the details. So how do we best exploit all that prior information? So we've seen things like SDS, score distillation sampling, and the previous talk talked about really impressive large reconstruction models. But we've looked at it even what I think is a simpler way of trying to incorporate all this prior knowledge, which is just do it at the loss level. So in addition to reconstructing pixels, we run a whole slew of other models on these pixels and treat them as observations. So we can segment out objects using things like track anything or segment anything. We can compute motion correspondences. We can compute pixel level descriptors like Dino. We can run depth models. We can run normal models. We think about all of these as observations of a video. And so now when we do our forward, rendering model, we don't just generate pixels, we generate flow, we generate Dino descriptors, we generate depth, and we generate normals. And we just add these as losses that we want to fit our representations to. And let's just say, so this body of work has really been led by a student, Gangshen Yang, over many years. And he's produced, I think, a really nice code base, Lab4D, that sort of supports one of the things that we hope that it would be at some point is maybe a version of Nerf Studio for dynamic scenes. But that really is up to the rest of you guys in the community to decide. And so one of the subtleties here when we add all these other losses and all these other observations of motion, of depth and normals, is we really have to know when can we trust those observations. And so a super important capability here has been using uncertainty estimates. And so what we found is amongst all of these different kind of modalities, motion has been one of the most important. So we have our own homebrewed version of optical flow that spits out uncertainty estimates, and only listening to the losses when we're certain about the measured flow has been super important. And then there's different deformation models. I'm happy to talk more about this, but again, we took the approach of really following what graphics folks have been doing. So there's something called, linear blend skinning models that try to model a deformation of some canonical space using, in this case, 20 control points or 20 Gaussians. And so we model the SC3 transformation of any point in space as a linear combination of these 20. And we can visualize these bones as they're moving around. And so this is from the perspective, I think, of a vision person, this is what graphics folks might do naturally to model deformation. And I'll throw out one kind of interesting technical bit that has emerged through these series of papers, which is when we're trying to optimize all these parameters, such as the deformation of the world and camera poses, the first thing that we tried was, okay, at every frame, let's hypothesize a camera pose, and let's try to backprop directly into this SE3 matrix that's represented for every frame. We found that was way too prone to local minima. And so there's this observation that Gangshen tried, which is instead of just directly backpropping into these geometric parameters, reparameterize them using a neural network. So at every frame, you just store a latent code, and you have an MLP that takes that latent code, a fixed MLP across all frames that spits out an SE3 matrix. And so now, instead of backpropping into the SE3 matrix, we backprop into the MLP and the latent code. So in a weird way, when Gangshen first proposed this, it was sort of strange to me because it seems like we're taking this problem that has a few number of unknowns, like maybe a 16 numbers, an SE 4x4 matrix for every frame, and now we turn into a problem we have many more unknowns, so we have a really big MLP. But it turns out that if you let's see, what's the right way of saying this? So one thought is maybe by having this over-parameterized representation of geometry, it's actually easier to optimize. And I think that's almost true, except that we have to add in biases to make this optimization a little bit more tameable. So for example, one thing we could do is you could have an MLP where you take as input a position-encoded time code. And so what this says is this adds a bias to the optimization that says nearby frames should tend to have similar SE3 transformations. Or you could instead have another parameterization where instead of processing position encoded time index, you could actually process the image and spit out a camera pose. So what this is almost training, it's training a pose estimator on the fly for the video of interest. And this adds this bias to the overall optimization that similar images should tend to have similar poses. And so I should point out that we've seen lots of really cool work that has popped up recently, things like flow map that apply this, I think a similar kind of insight where instead of training a pose estimator on the fly, they train a depth estimator on the fly. So still you're trying to almost re-parameterize this test time optimization, but in such a way where you add in these biases that in this case, similar images should produce similar poses or similar images should produce similar depths. Okay. And so the last piece of the puzzle that we've been super interested in is trying to really reconstruct dynamic scenes with very large dynamics. So here's a scene that I'll show you reconstruction for. So at this point, this is our local, it's our office. And so this student, this is Andrew, he's walking from one corner of the office to another with a dog. And so here, this is a pretty large deformation. And so the one underlying hypothesis I would have is for these kinds of large dynamic scenes, I would make the bet that the reconstruction has to be compositional. I think it's going to be hard to just think about this as having some canonical reconstruction, and I'm just warping everything I'm seeing here to this canonical structure. Instead, if you actually have sort of object-centric reconstructions where the objects themselves can move around with their own SE3 transformations, I think that'll be super crucial. And so the problem is that if you're trying to estimate sort of rigid-ish SE3 transformations of objects, even for deforming objects like that dog, essentially the problem is just as hard as inferring camera poses. So the claim I want to make is we have to understand what the front of this object is and what the side of the object is. And that's equivalent to almost like estimating, it's just as hard as estimating a camera. And so what we've looked at in a series of papers, this is led by Jason Yang and Amy Lin, is this problem of like object pose estimation in a category agnostic way. So if you just have a bunch of images of objects, can you estimate the relative position of the camera in object space for all these images? And my claim is that if you can do this, you can really solve these really dynamic reconstruction problems. And this requires estimating relative rotations and relative translations as well. Okay. And I just want to keep an eye on the time here. Okay, I'll sort of go through this body of work, which I think is kind of fun, and it's culminated in a I think kind of a fun piece of work, Cameras as Rays, that Jason and Amy just presented at iClear a little bit ago. Okay. The starting point is, okay, if we're going to try to train a model, all right, so how do we think about this in relation to the optimization that I just said? So what we're going to do is we are going to sort of build camera models that we'll use to initialize our test time optimization, the differentiable optimization I showed before. So we'll hypothesize cameras of the actual camera that's capturing this video sequence, and we'll also hypothesize object cameras that basically capture the rigid body motion of the camera, rigid body motion of the objects. In order to do that, we'll answer this question of, just by looking at image observations of objects from different viewpoints, can we tell what the relative translation and rotations are? Okay. The take-home message here is, well, let me dig into this a little bit. So the first is, how do we build models that predict cameras? And one starting point was this really wonderful piece of work called an implicit PDF. I'll press that again.
I think it's just negative charge.
Got it. Okay. Okay. So what I'll start with is this piece of work we were inspired by that said that try to train a neural network on data that would spit out the pose of an object. Are we looking at the front of a chair or the side of a chair? And the way that this piece of work actually did this, it was interesting. It formulated this not as a direct regression problem, but what this network did is you gave it an image plus a hypothetical pose, and it spit out a score. And then hopefully you train it so that if you give it the real rotation or pose that this object is imaged in, it should spit out a high score. And our starting point for thinking about this is, while this makes sense for objects that naturally have a canonical coordinate frame, like a chair, we can say there's a front and a side, and a top and a left. For some objects, it's really hard to define a canonical pose. But what we can do instead is define a relative pose. And our claim is that's almost always well defined. So what we're going to do instead is train a neural network that, given two images of an object under some transformation, it's going to be an energy-based model that will essentially tell us what is the relative transformation. And what we'll actually do is we'll train the network that is going to take as input two images plus a hypothetical rotation, and it'll spit out a score. And we'll train it so that it spits out a high score whenever that rotation is true. I'll skip the details of this, and we have a body of work that sort of builds this up where, if you do this, it's nice to use transformers that can even use information from multiple images. But the take-home message is that it's one of these energy-based models that you give it a bunch of images, and for every pair of images, you can hypothesize a particular rotation and translation, and this will tell you if that's good or not. And now you can solve an optimization that spits out the final set of rotations and translations. And this thing we're going to train on these 3D data sets such as CoMap. So one of the take-home messages is that this is something that we're actually pretty happy with. So we try this all the time on just random objects in our offices. And we encourage you folks to do the same thing as well. So there's a CoLab demo which is really easy to use. You just take pictures of some random pictures of a handheld object, put it into this network, and then it will try to spit out the relative placements of the cameras using this energy-based formulation. What this is a visual of the black represents the ground truth poses, and the colors represent the prediction. So this is if you run CoMap. And so CoMap will work if you have lots and lots of views of your object, on the order of like 50. But if you're on the order of less than 10, oftentimes it doesn't converge. And these are different models that we've looked at and compare with that. And you know, this is one example. The predictions of our energy-based model, the green cameras, are really close to the black cameras. Okay. But maybe one of the directions that we're really excited about this sort of work is trying to even sort of, I guess, ask this question of are there other ways to parameterize cameras that are even more amenable to neural search? And so here's this view of thinking of cameras as rays. And what this is a visual of is, for every pixel, instead of encoding an image, the camera of an image using a 4x4 matrix, let's instead encode for every single pixel array. And if all the rays are nice and they all intersect at one point, they define a camera frustum. So what we actually do is we train a neural network to spit out a pixel level dense prediction, which is the ray associated with the pixel. And now that we take all those predicted rays, we can essentially fit a camera to it. This turns out to be even a bit easier to fit, because we kind of know how to do pixel level prediction using our current architectures, you know, UNet style architectures or even VIT style architectures. One of the cool aspects of this is that you can actually, when you spit out the rays, this model can tell if you're looking at a wide angle camera or a fisheye or a barrel lens distortion, just because the rays will look different. And so this actually was a representation that was introduced way back in 2005, called a Raxel by Grossberg and Nair. This was actually introduced for the camera calibration literature, but basically it's saying that almost any imaging system, including crazy imaging systems using catadioptic mirrors, when you're looking at reflections off of parabolic mirrors, it can almost always be characterized that every pixel has a unique ray. So what's kind of cool is that now you could just have that be the representation of your camera, even of your pinhole camera. And that can represent things that aren't even pinholes. And now this is sort of trainable in a very nice kind of way, because we know how to do pixel level prediction tasks. So the take-home message is that now we can train these models that can spit out relative object transformations in these dynamic scenes. And this turns out to be super important for initializing these sort of inverse rendering optimizations for dynamic scenes when lots of things are moving. And so now I'll just show off some sort of fun visuals. So here's an example of a capture from your iPhone where you get both RGB, and because it helps the optimization even more, you can also get sensor depth. because all of our iPhones have that. The little third lens is it's actually a LiDAR camera. So what we can do now is using the techniques I just talked about, we can do a full heavy duty optimization that optimizes for the camera, the pose of the camera, the SE3 pose of the cat, and deformation parameters that fit all this data, including the image, the depth and flow, and all the other stuff I mentioned before. And now we can do, let's say, pretty aggressive novel view synthesis. We can say, what would the world look like if I had a camera on the ceiling? And I'll show you in a second as we move around, you'll see the cat move around. But I think what's really cool is you can do stuff of, because we reconstructed the motion of the cat, we can actually put a virtual camera right in front of the cat's face. And this is what that virtual camera would see. And we can even put, this is the virtual camera that we've drawn in yellow. We can also put a virtual camera right behind the cat. It's almost like a little selfie drone that's following the cat as it moves around. And because this is done over this video, we can render this thing. So it's kind of a fun example of what the cat is seeing as it's moving around the ground. Over here, that blue camera is inside the floor. So it's a little, it'll pop out in just a second as the cat is moving. But again, this is just differentiable optimization on this one video on the left-hand side. So the challenge I wanted to say is, how much can we do just by trying to fit to the data at hand and not really rely on, I have huge 3D repositories of cat model shapes and sort of room geometry. This is just fitting to the pixels that are in front of this video. Here's some other examples. That middle video is one I showed before of the person walking around with the dog. This last video I like, this is Gang Shen, is he's walking around different rooms on the right-hand side. This kind of looks like one of these third-person shooter games as the person's walking around. And it's amazing how much you can see just from the single video caption left-hand side. So all those white pixels represent parts of the world that we didn't see. And so that's where I think we should rely on prior knowledge and SDS and sort of, I've seen other walls and other rooms. And so that gives me a really good guess about how I should fill in these pixels I don't quite see in the actual video in front of me. And we've extensions of this, using Gaussian spotting to make it super efficient. So I somehow like this idea of, instead of just picking random viewpoints to render, pick the dynamic objects, interesting dynamic objects in the scene. So what I'm showing on the bottom left-hand side is this is re-rendering this dynamic scene from the point of view of the ball as it's spinning. And here I should say we're using, in order to get this level of fidelity, which still, we're not fully there. There's lots of artifacts here. It's using many, many camera views, but it's still applying the same differential optimization perspective. Okay. And maybe I'll sort of throw out like one more sort of pie in the sky vision here. So we know that if we really want to solve the 3D problem, one of the general phenomena that we're seeing is scale is our friend. And we desperately want to build lots of, 3D data sets for training. And so one hypothesis that we'll never be able to, okay, here's a claim I'll make, and it might be true or might not, but we'll never be able to kind of build 3D repository assets at a scale that rivals what we see for images or text. So instead, and perhaps one of the places that we've done this most closely is 3D assets for people. We're more focused on 3D reconstruction of people than probably another category. And there's been a lot of incredible work done in that space. But it seems like that's going to be hard to replicate for animals, for other sorts of deforming dynamic objects. But we have videos of them. We can download arbitrary YouTube videos. So we can push this approach of really 4D reconstruction from videos. Hopefully we can build, we can essentially, instead of requiring large 3D registered scans of dogs or cats, we can just take downloaded models of these videos and try to build these 3D assets. So we have some work in this space that sort of hints at this direction, but clearly we're nowhere near the full vision. And so the hope is maybe we can use these 3D assets or 4D assets that are fit to videos as the large scale repository for learning foundational 4D knowledge. But that is kind of a pie in the sky claim. Let me skip this for the moment, and maybe I'll sort of end here. So hopefully the take home message I'd love you guys to walk away with the first part of the talk on sort of large scale reconstruction. Essentially, what we're exploiting there is like good old graphics knowledge about using visibility constraints, using pyramidal representations, representing the world as surfaces versus volumes. And my hunch is that there's still more to be said there, even though, you know, we can definitely push the machine learning perspective by adding more transformers and other architectures. I feel like in the world of reconstruction, there's a lot of graphical insights that are still remain to be exploited. For dynamic reconstructions, the place that we really tried to put in all this prior knowledge was additional loss functions that extracted all this other descriptors and normals from the videos that we're trying to analyze. And one of the crucial pieces of the puzzle is really getting good initial estimates of cameras, both of how the recording camera is moving and as well as object level pose information for truly dynamic objects. And so there's that whole kind of, I guess, a great deal of effort of getting good relative camera pose predictions. And then finally, I think there's sort of fun applications of the fact that we all have multimodal sensors like depth and RGB that we can show off some sort of fun novelty synthesis. And with that, we'll conclude. Thanks.
Thank you, Professor. We have a couple of minutes, maybe 7 minutes for question and answer. So please, if you have any questions, let me start by maybe to motivate other people to ask. So you saw the Duster, actually, Jerome and Vincent were just here.
Yeah.
The authors of Duster. What do you think of that, learning this stereo system that's trained on a lot of 3D multi-view data sets in order to estimate the camera poses versus, for example, the cameras as Ray's great work that you have?
Yeah. So I think it's all very similar in spirit. So you can almost think about the rays as if you, instead of predict a ray, you try to predict a ray segment or a line segment, then I think it almost looks very Dusterish. So I think that makes a lot of sense. So in some sense, I think Duster can make the same kinds of arguments. They could actually encode distortion in the way that they represent things. They could tell if they're looking at a wide angle lens or a wide angle camera or a normal camera. I guess the open question to me is like, if we have enough rich data to really train that. And I think that's one of the real, I don't know if they're still here, but like the impressive thing they did is like they put together the training data set that was really diverse and figured out a good way of sampling to get a good signal for training these things. But yeah, so I think that still is sort of the challenge.
So in terms of training models, I see a lot of late multi-view diffusion models. For example, Cat3D use cameras as rays, like as a representation instead of the camera, like matrix basically, and it seems to work very well. So it would be interesting to see how, for example, training large system on these representations directly, similar to how Duster did, but with the new representations.
Yeah, definitely. I think that'd be super cool.
Any question, please? Yes.
Hi, yeah, thank you for the very nice presentation. I have two very brief questions. So for one, for the large scale reconstruction, you showed some really nice visualizations of also the geometry, and like the surfaces look pretty sharp. So my question is a little bit, for example, if you have drive-through videos from the city, then I guess the one of views you have, for example, more uncommon views. I mean, the observations are very rare. And then I found it quite surprising that the geometry still can be that good. Are you using any priors like depth predictor networks there as well? Or is it really all just optimization based? And if so, are there any tricks that make the surface more like uniform and so on? And the second question would be, like, for example, the dynamic reconstruction and so on. So usually you have an entire video and then you optimize, but for example, I guess in a robotic setting, a lot of the stuff has to happen online.
Yeah.
So the question is, are you also looking into kind of online prediction where you learn from a lot of existing videos and then combine with on-the-fly optimization?
Yeah, great questions. Let me start with the second one, which is a little bit easier to answer. So clearly all of this stuff, even though I'm sort of motivated from a robotics perspective, these optimizations are way too slow right now to actually do on robot. Although we do have some examples of like training Gaussian splats that could be real time. So there's a SLAM paper using Gaussian splat reconstruction, SPLATAM, that is real time. So I guess there's a chance of making them online, but the involved reconstructions I'm showing here took many hours. So that is one of the approaches of almost trying to do this kind of foundational story of do this all heavy offline computation. Think about these as really nice, juicy labels for then learning supervised fast, feed-forward students. So we have some initial work in that space. So this is an example of that exactly. So you do a heavy offline optimization, you just train a feed-forward student that takes milliseconds, and so then you can do this in real time. So the thing on the right-hand side, you could run on a robot. But I think the challenge there is really training at scale where you can actually learn sort of a rich diversity that allows you to generalize. So when you run this thing on a robot. The first thing you're saying is also super interesting. Like, so how are we able to get like high quality reconstructions at scale? Particularly when we're limited with ground viewpoints. So hopefully you buy the argument that if you have aerial viewpoints, that helps a lot because you get to remove a whole bunch of the occlusions. When you're in the ground, yeah, you have a building in front of you that you can't see beyond. One of the big wins there for a lot of autonomous vehicle fleets is that you get multimodal data. You get LiDAR sensors as well, which is huge. So what I find kind of surprising is a lot of the work that we're seeing don't actually use that multimodal signal. And I think one of the reasons why is that it's really hard, practically speaking, to calibrate different modalities. And in fact, there's a beautiful piece of work, NewRad, that is at CVPR, not ours, but we're working on a similar thing that they published first, that points out that one of the reasons it's been really hard to align different modalities is that like LiDAR and cameras are actually technically rolling shutter sensors. So LiDAR actually takes 100 milliseconds to do a sweep. So it turns out that if you model, like, I think one of the big reasons people don't get high accuracy by naively putting these different modalities together is that you're sampling rays from different positions at different times. But if you model that correctly, you actually get a way richer signal out. And so this paper does exactly that. So I think that like it's sort of a lesson of if you're gonna do all this sort of sensor stuff, like it seems like this kind of ray-based view of the world is a really nice way to integrate different modalities.
More questions?
Yeah.
Yes, please.
Yeah, thanks for the nice talk. My question is maybe how do you compare with the learnable method to activate camera process? You have the raw paper that directly regress on the notations and maybe translations. And we also have like the flow map style that use pro process that implicitly solve all the stats and correspondences. Yeah. So how do you compare with them?
Yeah, that's a great question. So somehow I think the closest thing we have to like a foundational geometric model is a depth network. And so for that reason, so for example, we have yet to train RelPos or cameras as rays at a scale that a depth network is trained. And like I said, I think that's one of the things that Duster did right. Like they trained at that very large scale. So to me, I think I don't quite have I think all the architectures are really similar. I don't know if this is a fair statement when the Duster folks are. I think of Duster as like a really powerful monocular depth network. They might disagree, but I think about cameras as rays is almost like an approximation of that as well. So I think the representation wise, to me, they're similar. The big thing in terms of the code that's out there is that they've been trained on very different data. So, I mean, it's the standard story of, training on more diverse scale and richer data. So I think that's the bigger knob than the representation, because I think the representations are kind of similar.
All right.
All right.
Thank you.
Thanks.
Hi, everyone. My name is Senem Velipaşalar, and I'll be presenting our point of view, which is a few-shot 3D point cloud classification network that fuses information from point cloud data as well as multi-view depth projection images. So very briefly, few-shot learning aims to find similarities and differences between the samples of a class instead of focusing on class-specific features. And then so far, joint use of 3D point clouds together with projection images for few-shot learning and few-shot point cloud classification has been relatively underexplored. So compared to supervised learning, you only need a very small number of annotated samples for inference, because few-shot learning tries to mimic the way the humans are learning. And then again, in contrast to supervised learning, with few-shot learning, the classes in the test set and the training set do not need to overlap. So it allows the model to generalize to never before seen classes. Now, the question is, why should we use both point clouds and projection depth images together to solve the few-shot point cloud classification problem? The answer lies in the matching nature of few-shot learning, because you want to match the query sample with a sample in the support set. And then, so the problem is that point clouds, as you see here in these pictures, they often suffer from occlusions and missing data. Like the two vases here, one misses points on the left side, one misses points on the right side. And when you try to match these together just by point clouds, that would create a problem. On the plus side, point clouds obviously is containing a lot of original spatial information and internal structure about an object. Now, depth images, on the other hand, as you see in this picture, the depth image obtained from the right view angle of the top vase and the left view of the view angle of the bottom vase, they still look similar to each other. And that will allow us to be a little bit more robust against these missing point issues. But on the negative side, point cloud projection process is being affected by view angles, and information is inevitably lost during this projection process. Now, considering the complementary nature of these two modalities, we propose point of view, which is a two-branch backbone for few-shot 3D point cloud classification. So for the 2D depth image processing branch, we propose a two sub-branch structure which aggregates individual image level features as well as features from groups of images, which provides us some global context. And we also propose something called multi-scale 2D pooling, which can learn local spatial features at different scales. For the 3D point cloud branch, before starting the processing, we sort the point cloud along the gravity axis to effectively learn part representations. Now, this is the two-branch architecture. The top branch is the 2D multi-view learning branch, and the bottom branch is the 3D point cloud learning branch. For 3D point cloud learning branch, again, as I mentioned, first the 3D point cloud is being sorted along the gravity axis. Then it's sent to a well-known, commonly used point cloud processing backbone called DGCNN. And then the output goes to pyramid pooling to obtain the point cloud features. Now, the 2D multi-view learning branch has two sub-branches. The top branch is image level, which processes the 6 depth images that we obtain from a 3D point cloud individually. And then the group level sub-branch is using features from groups of those projection images via a process we call view pooling, which I'm gonna go over a little bit more. And then this goes through, after these features are combined, it goes through a smoothing operation to alleviate the aliasing effect, and then goes through the multi-scale 2D pooling to give us the multi-view depth image features. And then these two features are concatenated at the end. Now, what you see on the left is the structure of pyramid pooling, which is something we proposed in a prior work. So what it does basically is it splits the feature map into different splits. The numbers are 1, 2, 4, 8, 16, and 32. And then global max pooling and global average pooling are applied splitwise. And then concatenation is performed along the split dimension. Now, since the point clouds are not sorted or ordered, a split that we are obtaining in the feature map does not necessarily correspond to a certain part of the point cloud. So to alleviate this issue a little bit, we perform this sorting operation so that there is more correspondence in the feature map splits and the parts of an object. And then here is the structure of view pooling. So basically what view pooling does is that it combines 6 feature maps in 5 different ways. So 3 of these ways are the combination of views obtained from opposite angles, basically. Don't let the words left, right, or bottom confuse you. It's just views from opposite angles. And then 2 are 2 triplets, top, front, and left, and bottom, back, and right views. And this is the structure of the multi-scale 2D pooling. So what we are doing is we are performing 4x4, 8x8, and 16x16 max pooling and average pooling, and then reshaping the outputs and concatenating them to fuse local and global features. So we use, in our experiments, we are using these 3 well-known data sets. And among these data sets, ModelNet 40 is known to most of you, probably is the simplest one because it's obtained by sampling CAD-generated meshes, so it doesn't suffer from missing points or occlusions. Scan object, and then on the other hand, is collected by scanning real-world objects, so it's the most challenging one among these 3 data sets. So here are results on the top on the ModelNet 40 dataset, and the bottom one is ModelNet 40C. So ModelNet 40C is a bit more challenging than the ModelNet 40 because it includes, it tries to simulate occlusions and real-world problems, but through simulation by using the same classes that exist in ModelNet 40. So our point of view approach is outperforming all the baselines over here. And here are the results on, again, ModelNet 40C is on the top, scan object NN is on the bottom. I wanted to keep 2 tables here at the same time because as you can see, on the scan object NN data set, the improvement margins are much more significant, which is the most challenging data set, compared to the ModelNet 40C, showing that our approach is indeed able to create a better representation of the 3D point clouds. Yeah, I'm done almost. So we also done one last experiment for cross-domain where we trained on ShapeNet, tested on scan object, or trained on ModelNet 40 and tested on scan object. And again, you see the performance. And one question I sometimes get from a prior work is how does the number of views affect the performance? Because in this work, we are using 6 projection images. So in this figure, you see that you see the results obtained with 6, 8, 10, and 14 views. As you can see, 14 views is providing a slight improvement, but this improvement does not necessarily justify the computational complexity of trying to process 14 views instead of 6. So I would like to thank you, my students who actually performed this work. And then we will be poster number 60 this afternoon if you have questions.
Any questions? So I have a question.
Yeah.
Given that I worked on point cloud
followed by a coffee break until 3:30. So we will resume the next keynote here at this room at 3:30. There is a vote and poster paper best poster award. So please look around the posters. We have 25 posters, a lot of posters, and vote for the one you like the most, or multiple ones actually. You can vote for multiple ones. And there will be awards at the end of the workshop for best papers.